Okay, welcome to Chapter 6 of the C++ programming language by Stroustrup. Chapter 6 refers to types and declarations, and we are skipping chapters 1 through 5 because 1 through 5 is basically like an abbreviated version of the rest of the textbook. Like chapter 1 maybe focuses on the content from like chapter 6 through chapter 12 or something like that. So 1 through 5 we're kind of just jumping over, we're starting with chapter 6. Chapter 6 is titled Types and Declarations. That is one of the more fundamental things to know about the C++ language. So the chapter begins by looking at the ISO standard. ISO standard. So we're not really looking at the actual writing of C++ code yet, but essentially the ISO standard is more of a description of the rules that a C++ kind of has to take. So ISO standard describes what is expected and not expected from a C++ implementation. And there's a couple of things to take away from that. The first thing is, what is a C++ implementation? When I see the word implementation, the general thing to think about is the specific tools such as a compiler that allow us to write, compile, and execute C++ code. So there's all sorts of tools involved, but I think the easiest thing to sort of think about is the compiler, like that translator. There are sort of different compilers that exist. For example, you can have, there's the GCC compiler, and there's the C-line compiler or Clang compiler in the world of C and C++. And so these are basically two different translators. And while they pretty much do the same job, you can imagine like with any kind of translation job, there might be some sort of slight variations in how something gets translated. Like, for example, if I'm describing like a round object, for example, one person might describe it as a ball, right? Might translate that to ball. Someone else might translate it to sphere. So the meaning is the same, and so both translations are valid. But if you look at the sort of technical detail, there's a slight sort of technical difference in the translation. So you can imagine there are different sort of quirks, I guess, in each translator. And so in that sense, you can have different C++ implementations. The other thing to think about is behavior. We're going to describe different types of behaviors that C++ implementations can take. But what behavior refers to is basically how a line of C++ code, not necessarily a line, any kind of subset of C++ code, how it should be interpreted or translated and executed. Okay, so we're going to talk about the different types of behaviors that are possible in the world of C++. But yeah, so it's a good thing to start by understanding what exactly a C++ implementation is, and then what behavior kind of refers to. All right. So from there, we look at types of behaviors that exist. So we have several types. The most sort of simple one, I guess, is well-defined behavior. Behavior is considered well-defined if, for a particular line of C++ code, there is consistent behavior across all implementations, C++ implementations. That is, for particular lines of code, the standard says there is only one kind of behavior that the implementation should take. There's one sort of result that should happen. So as an example, if you asked in C++, what is 7 plus 3, you somehow use an arithmetic operation in some line of code, the standard says just apply normal mathematical operations there. So all implementations, all C++ implementations will return 10 for this particular instance. There is no sort of variation in that. So that's well-defined behavior. You can expect the same thing every time. Next, we have implementation-defined behavior, and this is where things get a little bit more interesting. And this is probably the most important behavior to understand because it's the one that gets mentioned the most, I think. Behavior. So implementation-defined. What does that say? What does that mean? Sometimes, for a particular line, C++ code, the standard, the ISO standard, allows for one of multiple behaviors, or I guess translations. So this is where like that ball versus sphere kind of example probably is most relevant. So the ISO will sort of suggest a few behaviors you can pick from, and it's up to the implementation to pick which behavior to do, basically. So the other important detail is the implementation must document which behavior it chooses to use. Okay. So as an example, this is actually a bit more of a complex example, but and it's an example that comes up later. So if it doesn't make a whole lot of sense right now, it will make sense later. But if you were to write a line like char C equals letter A, that might seem like a simple line. Essentially, we're creating a character variable and assigning the value of the character A to it. But under the hood, the standard says for character types, they can be represented as either signed or unsigned. Now, what does that really mean is something we'll get to, but what's important to understand is the standard suggests multiple behaviors, right? You can either do this one, or you can pick this one, right? Signed and unsigned you can think of for now as just different options for interpretation to pick. And so for a particular implementation, so a particular implementation might say, I'm going to choose the signed version, or the signed behavior. So the standard offers a few multiple behaviors to pick from, and the implementation must document which one it's going to do. And that's the process of implementation-defined behavior, having this idea of you have multiple options, but you must document which option you pick. All right. That's to contrast slightly with, that is to contrast slightly with unspecified behavior. I'll keep this here because I think it's good to have. Unspecified behavior is quite similar. Unspecified behavior is similar in that the standard offers multiple behaviors to pick from, but this time documentation is not required from the implementation. Implementation. So, for this one, for implementation-defined behavior, you must actually tell, the implementation must actually say which behavior it's going to do. But for unspecified behavior, documentation is not required. So an example for that is the order of evaluation of function arguments. So the order of evaluation of function arguments. That might seem a bit complicated. And to be honest, functions is something that we look more at in chapter 12, I believe, so it's a little while away. But in general, you can think of a function, if you're really uncomfortable with the concept of a function, think of a function as a sort of little packet or block of code that can be called upon to run whenever you want, essentially. And you can run it multiple times. Whenever you call it, it will run. And you're also able to provide it with data, which we call arguments. Each piece of data we call an argument that you're passing to the function when you ask it to run. So, for example, if there's a function f, which exists, right, I might call the function by doing something like this, and I might give it some data, some arguments like this. I might give some 3 plus 7, 6 minus 2, 1 minus 3, for example. And I could have very easily just written 10, 4, and -2, but I want this idea of I need to evaluate the arguments before I can pass them to the function to use. So when you run something like this, I'll put a semicolon for the sake of argument. When you run something like this, the arguments have to first be evaluated to figure out the actual value before you can actually run this block of code, run that function's code. So, especially if you sort of are comfortable with a language that reads from left to right, you might think that, well, naturally I'd probably start with that one, evaluate that, figure out that's 10, then go here, figure out that's 4, then go here, figure out that's -2, and then pass everything in. But there's nothing in the standard that tells you have to go from left to right, or right to left, or anything. Technically speaking, the implementation is allowed to go in whatever order they want. If they want to start in the middle, evaluate that, then go to the end, then come back, it's allowed, and there's no expectation to document the idea that you do something like that. And the reason for not needing to document is because that kind of detail shouldn't really affect a programmer's code. If your program really relies on the order of evaluation somehow, it's likely that your code will break on a different implementation, on another machine, for example. So that would make your code quite brittle. So you should never really have to rely on unspecified behavior on how it works. So that's why documentation isn't really required from the implementation. Now the last one, which is kind of the scary one, is undefined behavior. Alright, so undefined behavior. Not to be confused with unspecified. Undefined has a separate definition. Undefined behavior has a separate definition. So, essentially, undefined behavior refers to lines of code that have no reasonable translation. Lines of code that have no reasonable translation. The standard gives no list of behaviors to pick from. Before the standard was telling us how to behave, but for these kind of lines of code, there is nothing. The standard can't really give anything suitable. So I think we'll start with an example, actually. So a typical example is if you try to divide by 0, so division by 0. So if you do something like 1 divided by 0. In essence, if you do something like this, where there's no real way to give a reasonable behavior, there's no reasonable translation, what I would say is there's absolutely anything random could happen. And I think I have a sort of example program where I do try to divide by 0, and I print the result, and something absolutely random will happen. There is no documentation, right? Similar to unspecified, there's no documentation, and there's no sort of reasonable behavior that could happen, right? So undefined behavior is something you should never engage in because it's not reliable, and it it doesn't even make sense, right? And it most likely will result in some kind of error or bug. All right, so that's that part. That's the ISO standard. There's 6.1.1, which talks about sort of the different types of implementations, but I haven't really found that super useful yet. I haven't found it super useful yet, like in terms of reading the rest of the book. So I think I'll skip it for now. If that ends up being a mistake, I will mention it at some point in time. But for now, I don't think it hasn't been very worth understanding that part. So I will skip ahead to 6.1.2. 6.1.2, which is on the basic character set. Okay. So when you think of basic character set, you want to think of like the characters that are sort of most common. And this is a little bit English centric because if you have a standard sort of US keyboard or European keyboard, that's kind of what you see on that keyboard is kind of what's considered the basic character set. So like uppercase English letters, lowercase English letters, the numbers 0 through 9, some of the punctuation marks and symbols you see, and there's a few other weird ones as well. So maybe I'll start there. So the basic character set consists primarily of English. Should always be specific. English uppercase and lower case letters. The numbers 0 through 9, symbols like the @ and the percentage sign, punctuation symbols as well, like full stop and exclamation mark and things like that, and a few weird ones. Some white space, new line, backspace like that, and a couple of extra ones that are probably not worth talking about right now. So that's what the basic character set consists of. That's how we define it. There's something called an ASCII table, which is essentially a table which maps each character in the basic character set, maps each character to a specific integer. To a specific integer. So there is a one-to-one relation, a bijective relation between a character and its and an integer. So I'll probably have a ASCII table on screen, and I'll split off the columns. So like, one column will be the character column will be one color, and the corresponding integer column will be a different color. And to read this table, for example, if you were to look at the character D, that would map to the integer 100. So the character D, lowercase d, maps to the integer 100, right? And the character 7, not the number 7, the character 7 maps to the number 55. I hope. Now, if you look at the ASCII table and you look at how many characters are in the ASCII table, you'll see that the numbers range from 0 to 127, which means there are 128 characters in the ASCII table. Okay, we can represent each of the numbers, so like the 100 here or the 55 here, we can represent each of these numbers. We can represent each number using 8 bits, so 8 binary digits. So if we ask, just as a quick sort of aside, if I asked how many sort of unique numbers can you make with 8 bits, the way I would kind of show that sort of naively is if you had 1 bit, you have 2 numbers you can give, right? You can have a 0 or a 1 if you have 1 bit available. If you have 2 bits, then for the leftmost bit you have 2 options, right? Like a 0 or a 1. And then for each digit within here, you have 2 options here. So for 2 bits, sorry, I got interrupted. So for 2 bits, you have 2 options here, and then for each option you have 2 options. So that gives you 4 options total. So you have 1 option, then 4 options. For 3 bits, you have 2 options, and then for each of those 2 options, you had 4 options for the 2-bit part. So that gives you 8. So every time you add a new bit, you essentially, sorry, this was 2, then 4, then 8. Every time you add a new bit, you double the number of possible numbers you can make. So for 8 bits, you have 2 options, and another 2 options, and another 2 options. Continues to double. And in reality, this becomes 2 to the 8. 1, 2, 3, 4, 5, 6, 7, 8, yeah. And that becomes 256. So we need to be able to represent 128 characters. And with 8 bits, we're actually able to create more than what we need. We can create 256 unique integers. So we actually have more than enough. And you might ask, well, is it possible to actually just use 7 bits? Can we just sort of, cut off the 8th bit and use it for something else? And I guess the numbers would work because 2 to the power of 7, does equal 128. So that would be more or less wasteful, you could argue. But when we think of 8 bits, we normally associate that with 1 byte. And the byte is the smallest unit of memory that we address individually. Each bit doesn't have its own independent address. So we tend not to split apart bits within 1 byte. We tend to keep them together. So, yeah. So that's 6.1. And then from there, we can move on to 6.2. Okay, so from there, we've done 6.1. So now we move to 6.2, which refers to the actual types. And so the word types is basically the description of what type of data we are dealing with, essentially. So the way the subchapter introduces itself is looking at the fundamental types, which is the types that come bundled in with C++ without us needing to sort of do any extra work. So the way that I would probably represent this is using kind of a growing Venn diagram type thing. So the types that we look at, in particular, we can start with the Boolean type. I don't bother writing type. Booleans, integer types, and character types. And these, green short, well, yeah, that's fine. These make up what we call the integral types. Right, so Boolean, integer, and characters are part of the integral types. Then you get floating point, or you can think of decimal number, floating point types. And the integral types, and with the floating point types, makes up the arithmetic, or the number types. From there, we have the additional type void, which is which kind of represents the absence of a type. And all these guys together make up the fundamental types. So these are the types we will focus on first. Fundamental types. So everything in the red is probably what we'll focus on primarily in this chapter. I'll just write that a bit better. Fundamental types. So these are what we'll focus on primarily. There is also arrays, which kind of is more about a collection of types, but the book doesn't really classify it in any particular way, it just puts it on the outside. And there's also user-defined classes. So we have things like classes, structs, if you've seen a bit of C before or you've worked with C++ already, then structs is something you might have seen before, and enums, or enumerations. Again, it's something we'll look at different time, but these are called user-defined types. And then, just to wrap everything around the universal set, all these things we see, all these things we've seen on the board, we are just generally speaking, these are our types. Right, so everything on the board is a type, and then some of them can be broken down into more sort of smaller subsets of types. And this chapter primarily will focus on the red stuff. Okay. So we start by just looking at the integral types, the green ones. Yeah. So we start with 6.2.2, which is Booleans. Hopefully, most people are relatively comfortable with what a Boolean is, but just as a refresher, maybe as a warm-up, Booleans are data types which will either store a true or a false value. So, storing true/false values. It is possible to express results of logical operations. So things like and, or, if you've seen sort of Boolean algebra before, we are able to construct Boolean kind of expressions which will evaluate to either a true or a false value, and then we can assign that to a Boolean variable. So Booleans are all about true and false, and it is possible, one of the bigger details to keep in mind, it is possible to convert a Boolean into an integer. And this idea of converting, let's write that bigger, integer. And this idea of converting between types, right, Boolean type to integer type, that's called casting. So casting is basically converting between types. So, you know, the Boolean set consists of two elements. You either have false or you have true, and the implicit conversion from Boolean to integer says that false maps to 0 and true maps to 1. So under the hood, the way false is represented in a computer is it's represented as a 0, and true is represented as a 1. Now there's a few other conversions that you can get, some few other casting things you can get. If you were to convert an integer into a Boolean, it turns out the way that it's defined is a 0, the integer 0 maps to false. Right? So if you were to ask what is the Boolean sort of equivalent of the number 0, you would get false. And any other number, any other integer, I should say, any other integer, whether it's positive or negative, so positive 42 or negative 13, will always map to true. Right? So we can actually kind of evaluate integers in the same way we would evaluate Booleans by doing this implicit casting, this conversion. This is true, by the way. The glare is kind of... That didn't help. That says true. I just won't use the bottom of the board. And finally, the last sort of conversion that's mentioned is pointers to Booleans. Again, some people might not be super comfortable with pointers yet, and that's fair enough. But for now, just to have it in the back of the mind, there's a pointer called the null pointer, which is the pointer that essentially points to nothing. And again, that will make more sense in chapter 7 actually. But for now, we have this construct called the null pointer, which maps to false, and this idea of any other pointer maps to true. Okay? And so the main pattern to take away more than anything else is when converting another type into a Boolean, when casting it, generally if you have this idea of like a nothing value or a 0 value, a nothing value, that will always map to false, and then every other element in the set of integers and the set of pointers and set of whatever will map to true. So this kind of conversion from sort of a more complex type to Booleans is usually, that's the kind of pattern you get. Alright, so that's Booleans. Then we jump straight into character types, and character types, unfortunately, are slightly more complicated. Alright, so when you think of a character, you want to generally be thinking of letters, right? Or sort of, yeah, symbols. Character types. So there's a few different sort of character types you can get. We have the sort of fundamental char type, which is, I'll just say usually, most often, 8 bits long. Right, in terms of size, how many bits are used to represent the char type? Typically it's 8 bits we use. And we talked about that when we talked about the ASCII part. We have signed char, which is like a char, but guaranteed to be signed. Signed meaning it either has a positive or negative sign at the front, right? We'll talk about more about what that is, what that means, or what that sort of implies in a second. You then have unsigned char, which is like a char, but guaranteed to be unsigned. So unsigned meaning there is no negative or positive sign, so you kind of assume that the number is going to be positive all the time. You have wchar underscore t, which is essentially this sort of additional character type, which is provided to hold characters of a larger or extended character set. We talked about the ASCII character set where there are the letters, the numbers, and whatever, and we only had 128. But of course, there are far more characters in the world, so we might need more than 8 bits in that case, and that's where the wchar t type gets used. So just as an additional note, the size of wchar t, so how many bits are provided for it, is implementation defined. So that's an instance where something can be implementation defined. The implementation kind of has to choose how many bits they want to associate with wchar t. Is that big enough? Wchar t. All right. There's also our char 16t, which is what you use if you want to sort of be a bit more specific about how many bits you want to use. So holds 16-bit characters. And char 32t, which similar but holds 32-bit characters. All right. Now, since a char typically holds 8 bits, right? There are 8 binary digits associated with a char. It can hold one of 256 values. That's what we said before, right? When you have 8 bits, there are 256 kind of different unique options you can make out of that. Binary numbers you can make out of that. Now, a char will either be signed or unsigned, depending on implementation. And this is something else that is implementation defined. The standard says a character can either use signed representation or unsigned representation. You can pretend that the numbers that characters are associated to, right? Think of the ASCII mapping. The numbers that characters are associated to, you can either think of as signed or unsigned. So depending on that, a character will actually be synonymous to either signed char or unsigned char. But without looking at the implementation documentation, you don't actually know which one it is, right? It will always be either the same thing as a signed char or an unsigned char, but different implementations will pick which one they want it to be. Okay. Now we look in a bit more detail of signed versus unsigned. This is 6.2.3.1 signed versus unsigned. Alright. So an unsigned char, meaning no sign in the front, so you assume positive, can take a value from 0 to 255. So I'll just talk about that in a bit more detail. Remember, we're using 8 bits here because it's a char type, 2, 3, 4, 5, 6, 7, 8. What's the smallest number we can make, right? The smallest number we can make is all zeros. Okay? And hopefully that's kind of intuitive that this represents the number 0 in our regular counting numbers. All zeros are the same thing as just our normal 0. What's the biggest number we can make? 3, 4, 5, 6, 7, 8. The biggest number is all ones. Okay? And that might not be as clear, but this number is the same thing as 255. And if you're not comfortable with binary, my advice for now would just be just Google it. Just confirm this is true using Google. And basically, every number in between can be created by some kind of combination of zeros and ones, sort of between the lowest and biggest extremes. So we can make the numbers 0 to 255. Okay, that's for unsigned. And something to note is this has 256 values, right? How many numbers are between 0 and 255 inclusive? There are 256. So there's 256 values possible here. Now, a signed char is very similar in the sense that it also has a kind of range of numbers it can take on. The major difference is that signed chars use positive and negative numbers. And in this case, the negative number, the range goes from minus 127 to 127. And what I'll tell you, you can confirm this yourself as well, is that this actually has 255 values instead of 256. Okay. For people who are a bit more comfortable with how negative numbers get represented in memory, and this is where sort of it gets a bit more complex. I wouldn't necessarily expect everyone to understand this part, but for those who are a bit more curious, so I'll call this extension. You might ask, well, why doesn't this have 256 values associated to it? You know, why doesn't the range, why not 128 to 127, which would have 256 values in it? It's to do with the way that computers represent negative numbers. Typically, we have 2's complement, but C++, the C++ standard, allows for negative integers to be represented using 1's complement, which is sort of a method of representing negative numbers using just bits, using 1's complement and 2's complement, which is like the more typical way of doing the same thing. But 1's complement is unable to represent the integer negative 128 using 8 bits. So because the standard allows for ones complement, it is not allowed to have minus 128 in the range, because ones complement is unable to express negative 128 using 8 bits. That method of representing a negative number, ones complement isn't able to represent negative 128. And that's all I'll say for that, because I think if that's not clear, then that's more of an indication that you need to there needs to be more study in ones complement, twos complement, which is a very separate thing and a very interesting thing, but not necessarily the main focus of this right now. The big focus is that you can either represent characters using positive numbers completely, or a mix of negative and positive numbers. Okay, that's the more sort of the bigger takeaway for now. Now, the difference between unsigned and signed, the difference in terms of their ranges, matters outside the 0 through 127 range. Hopefully it's clear to people that in both ranges, the 0 to 127, those numbers, 0 to 127, exist in both, right? 0 would kind of be in between here to 127. Here, 0 to 127 would be like from here to like the middle. So in both cases, the numbers 0 to 127 is present in both, and the characters associated with 0 to 127 is the same. So the way I would draw this is if I had unsigned versus signed, unsigned has 0 to 127, and then has 127 to 255, versus signed, which also has 0 to 127, but then instead of bigger numbers, it uses more negative numbers. It goes 127 to negative 1. And then the idea is the characters that map to the 0 to 127 in both cases are the same. And so it's ASCII characters from the table, right? ASCII characters. And it's only if you try to use other symbols or other characters that are exist in the world but aren't part of the ASCII table, that's where they get associated with the sort of other numbers in the range. So other characters get associated here. So if you were to use just ASCII characters, you actually wouldn't notice any difference, because you'd always be working with the range as 0 to 127. You wouldn't really care about, this should say 128, sorry. You wouldn't actually care about sort of whether the chart type is using more positive numbers or starts to use negative numbers. But if you try to use these extra characters in a particular character set, you might start seeing changes in behavior in terms of whether it's using big positive numbers or more negative numbers. Alright, so that's what I'll say about signed versus unsigned. Biggest things to understand is the representation of what kind of integer a character maps to might change, but it only really matters for non-ASCII characters. Now, we'll go back sort of outside, back to character types. And there's a few rules regarding characters and different character types in terms of how they can sort of mix together. So this again mentions pointers a little bit. So if you're not super comfortable with pointers, this might just be something to take on board, but not without having a super complete understanding. But the general rule is you cannot mix pointers to different character types. Okay, you cannot mix pointers. So imagine you have char c, right? It's the variable c of type char. Imagine you have signed char c. Sc. So the variable sc of type signed char, and unsigned char uc. So variable with the name uc of type unsigned char. So the way we're representing these things slightly changes. If I try to create a char pointer, PC, pointer char, with this type char pointer, that points to a char, and I try and make it equal to the address, ampersand means address, of UC, okay, this is unsigned char, and this is regular char, pointer, then this will result in an error. This was something that is not allowed. And so we get similar results if you try something like signed char star, PSC equals PC, right? PC is a char star, is a pointer to a char. This is a pointer to a signed char. So if you try to mix those together, you're also going to get an error. And similarly for unsigned char star, PUC is equal to PC again. Will cause an error because you're trying to mix a char star pointer with an unsigned char star pointer. It's going to cause errors. And PSC equals PUC. PUC again is unsigned pointer. This is a signed pointer. So trying to mix them together will cause an error. Okay? So if you're not super comfortable with pointers yet, that might not be something you take on board just yet, but it's something to just keep in the back of the mind. Pointers for char types cannot mix in terms of type. However, weirdly enough, even though that rule exists, there's a sort of opposite yet very similarly worded rule which says you can mix different char types, so without them being pointers, you can mix different char types, but if a too large value is assigned to a signed variable of signed char, this is not well defined. Okay, and I'll talk about what that means as we go. So imagine you have char C again, signed char SC, and unsigned char UC, and they're given some relative value, some character or some particular, they're put a particular value in their range is given to them. Char, remember, we do not know at this point if it's signed or unsigned. The implementation will choose that, so we do not know whether it's signed or unsigned. So just bear that in mind as we do this. If we try C equals SC, we're trying to assign the value of signed char to the value of C. This is okay because either C is signed, in which case they're both the same thing, so you can just give the value straight away, or it's unsigned, but because I guess the range of unsigned numbers is bigger than the range of signed characters, the conversion or casting from signed char to unsigned, or maybe potentially unsigned char is well defined. There's a very clear-cut method involved in converting, for example, negative 125 to the corresponding positive value that is outside the 0 to 127 range. Okay, so going from SC to regular char, completely fine, because either char is signed as well, or it's unsigned, but the conversion is well defined, so the compiler can happily handle that. If we have C to, change color. If we have C equals UC, this might be problematic. This might not be so super well defined. If C is also unsigned, remember UC is unsigned char. If C is also unsigned, there's no problem because whatever the value is here, you just give it to here because they're the same type. But there might be a problem. If C is signed, if C is signed, the conversion from what is a smaller range of numbers, negative 127 to 127, the conversion from unsigned the conversion from unsigned to signed is not well defined. I'm getting tripped out whether what signed means, what unsigned means. So signed means it has a sign out the front. So the conversion from an unsigned character to a signed character is not super well defined. Like there's no real way of doing that. So this might cause problems if C is signed and is trying to assign an unsigned char. SC equals UC I believe this is also a problem. So also a problem because for the same reason as above. Because in this case we actually know that SC is signed, so trying to go from unsigned to signed is going to be a problem. Because that conversion is not well defined. Going from a really big number like 255, trying to put that into the negative 127 to 127 range is not well defined. SC to C, UC equals SC. So this is basically flipping things around, right? SC equals UC, now it's UC equals SC. That's actually okay because we're going from the conversion from signed to unsigned. So being able to convert minus 127 and pushing that to that range of 0 to 255 is well defined. So signed to unsigned chars is well defined. And SC equals C, again, might be a problem if C is unsigned. If C is signed, then they're the same type, whatever values in C, you just give it to SC. But if C is unsigned, and it might be, then you're trying to give an unsigned character to a signed character, and so, like we said before, the conversion from unsigned to signed is not well defined. So that might be a problem. And finally, UC equals C is okay because either C is also unsigned, in which case we just give the value, or C is signed, but we said that going from signed to unsigned is a well-defined process. So no problems there. Okay? And semicolons. Yeah, the reason why it's easy to go from, it's well-defined to go from signed to unsigned, but not okay to go from unsigned to signed is a little bit low level. I'm trying to think. In essence, it's to do with the fact that because you have 0 to 255, you have 256 values, there is one value in that cannot be put into the negative 127 to 127 range because there's less numbers in that range. So I guess the way I'd write it is trying to go from 0 to 255, so the unsigned, to the negative 127 to 127, the signed. There's a problem because this has 256 elements, this has 255, right? That's how C++ shows it. But what that means is there's going to be one value in here that doesn't map to anything because all the other values have been taken already. So there's one left that you can't really do. So this is not well. That's why this is not well defined. Going from unsigned to signed, not well defined. Going from signed to unsigned is okay because this is actually a smaller set, right? There's less numbers here, so it's easier to match each number from here to a number here. So going the other way is okay, but going from unsigned to signed, like this, is going to cause problems because there's definitely at least one number in there that just doesn't have a buddy to link up with when it tries to map across. Okay, so the major takeaway is for this particular rule, signed to unsigned is okay, right? Assigning a value that's signed to an unsigned value is okay, but going from unsigned to signed is going to cause some slight problems. All right. What's next? Literals. Okay. Yeah, so there's a lot of stuff on characters. 6.2.3.2. 6.2.3.2 character literals. So whenever you see the word literal, whenever you see the word literal, you always want to be thinking about, I guess, instead of looking at variables, we're looking at the actual literal representation of a character. That might not make sense. I'll write down some definitions. So, a character literal is written as a single character enclosed in single brackets. Single quotes, Single quotes. And the type is defaulted to char. So maybe it's easier with an example. If you were to see something like, A with quotes wrapped around it, that would be an example of a string literal. We're not working with variables, right? We're not saying char C, and C is like a sort of variable that where things can be assigned to it. This is a string literal, a character literal, and its type, even though we don't say it, the compiler defaults this type to char. That's what it's saying. So we enclose a letter or a character in quotes, single quotes, then that's a character literal. Now, a few extra details which are a little bit low level in terms of quite sort of interesting. We can represent a character from the character set as, well, firstly, we can represent it as a integer, right? We've seen ways that we can map integers, regular whole numbers, to characters using the ASCII table, for example. But we can also use octal numbers, 1, 2, or 3 digit octal numbers. And octal numbers are similar to our normal numbers, except octal means base 8. So the only digits that exist are 0 through 7. So you think a binary is base 2, octal is base 8. And the way we represent octal numbers, at least for characters, is we do backslash followed by octal digits, and we also make sure to enclose this in quotes, single quotes. Right? We can represent using octal digits, or we can represent using hex digits, hexadecimal numbers, which would be a backslash and an X followed by hex digits. And hexadecimal is like octal, except it's base 16. So there are 16 digits in the hexadecimal system, and of course we enclose with quotes. And unlike octal, which specifies you can either have 1, 2, or 3 digits, there's actually no limit on how many hexadecimal digits you can use. Okay. In both cases, the number is terminated. It stops reading the number when we use a non-digit character within the quotes. I should not have done that. I guess just to give an example, for octal, you might see something that looks a bit like this. What's a normal octal number that I know? Maybe like 100. Okay, I know that looks like binary, but that is in this case an octal. I'm writing that as an octal number, and I believe this is the same thing as 64, right? 8 squared. This number here is 64. So what is the corresponding character? Maybe I'll just look at that. I'll look at the ASCII table real quick. So 64 is the @ symbol, right? So that I've done that conversion by looking at the ASCII table. The 100, which is the same as 64, if we look at like going from base 8 to base 10 is 64, that looking at the ASCII table, 64, I'll do it like that, 64 maps to the at symbol, right? So in that sense, we can use different bases, primarily base 8 or base 16, to instead write, use like a different number representation to still refer to characters, essentially. Yeah, that's pretty much what I'll do there. Now, we have something called a wide character literal. Sort of still within the discussion that sometimes we want characters that are not part of the basic character set, wide character literals. Basically, you prefix your character with a capital L, so it's of the form LAB. Alright, and these default to type W char underscore T. So whereas before the default type was char, this time we use the big char type instead. And the number of characters used and their meanings are implementation defined. It's my understanding that wide characters aren't really used so much anymore, so this is kind of just something to add, but I wouldn't necessarily look too much into it, but it's just that's there. And continuing this discussion, we can have larger character sets, so things that extend beyond the ASCII and even 8 bits, by presenting a sequence of 4 or 8 hex digits, hexadecimal, base 16 digits, preceded by a U or a little u. So I'm not going to look too much at the specifics of how hexadecimal works, but I will just show kind of how they are used in this context. So, for example, 2 examples that I had were, if you have capital U, and then sort of backslash U, then you have something like this. There shouldn't really be any white space here, I've just added it for clarity. The first capital U indicates that the upcoming character is going to be 32 bits. And the capital U here tells us we're going to expect 8 hex digits. Now, if you're really uncomfortable with hexadecimal digits, that's fair enough. But just bear in mind that it's 16. There's 16 digits, so you have 0 through to 9. 1, 2, 3, 4. And then, just out of choice, it was decided that the last few digits would be letters. So A through F, A, B, C, D, E, F. And all these are 16 digits that are used and represent sort of 0 through 15. Yeah? So this in itself is another number and would be associated with a particular character in something called Unicode, which is a whole separate thing. But it's essentially a type of extended character set or larger character set. So, but this would just be a number that would be mapped to a particular character in this larger set. And using the lowercase u, you might have something that looks a bit like this. So the first u indicates, I think, 16 bits, and the second u tells us to expect 4 hex digits. Okay. So that's kind of a way that we can use extended or larger character sets with these prefixes u and lowercase u, capital U and lowercase u. And I should add that the type here defaults to char 16, I think. No, wait, sorry, char 32. And the one here defaults to char 16t. Naturally, because by this prefix, this entire thing will require 32 bits, so the sort of appropriate type is this one. And for the lowercase u, that tells us it's going to be 16 bits, so it makes sense for the type to be char 16. Alright, and that's everything on characters. Right, so we're back. So continuing onwards, we've just done character types, and now we are doing integer types, the last integral type in our Venn diagram. So integer types come in three forms. You have int, signed int, and unsigned int. Right, so we have this idea of signed and unsigned again. And integer types, integers also come in four sizes. So you have short, sort of the regular plain normal int, long, and long. Four possible sizes for integers. And the plain ints are always signed. Plain ints are always signed. So this is something that contrasts with the characters. With characters, with the char type, the plain char type, it was implementation defined on whether it was signed or unsigned, the char type. Here, the int type, the regular int type, is always signed. Always. That's a well-defined thing. So something to note. The signed int type, that is this one, is actually just a more explicit synonym for the regular int. You could actually get away with never writing signed int, because int and signed int mean the same thing, because int is always signed. But if you want to be a bit more clear in your code as to whether the integer is signed or unsigned, you could write signed int. Is the idea. There is mention of a standard of a library called the standard int library. That's a library that you can include in your code, part of the standard library. And this includes types like int 64t, uint fast 16, t int least 32t. I won't go into too much detail as to what these are, but essentially they're more controlled types which specify things like how many bits are included and a few other details that I won't go into, but that is part of the standard library. And not much more to talk about in terms of the various ways we can express integers, but we will look at integer literals. So just like with character literals, which was about writing a literal character in quotes, integer literals are all about literally writing a literal integer. So decimal numbers. No. When I say decimal in this case, I mean base 10 as opposed to with a decimal point. Decimal literals, I meant, are just written as numbers without too much drama. So decimal in this case means base 10. So e.g., if I was to just write 1, 2, 3 or negative 1, 6, 16, that's just how you would write a literal in base 10. Hex literals start with OX, and then you would have your hex. You would have your hex digits afterwards, and then octoliterals just start with a 0, and then you would have your octal digits afterwards. So OX versus O versus just regular number, right? That's how you can express different types of literals. There's a few suffixes as well. So with literals, maybe I'll keep this actually. So the suffix U makes the integer of type unsigned. Oh, I should mention, yeah. The default type for literals is int, as you might expect. So the default type is int, but maybe we want to make it unsigned, right? Because the int is always signed. We want to make it unsigned, so we can put a capital U afterwards, like 1, 2, 3, capital U, just like that. And that would make it of type unsigned int, as opposed to the regular signed int. The suffix L is to make a long, so suffix L turns the integer into type long. So 1, 2, 3 L basically means instead of giving an int worth of bits, we're going to use a long's worth of bits. And the suffix LL just rewrite that, turns the integer into type long. So before we would have had something like, 1, 2, 3 L. Here was 1, 2, 3 U. Here would be 1, 2, 3 LL, and that would give a long's worth of bits to this literal. Suffixes can be combined. So it's right here. Suffixes can be combined. So for example, you have something like 1, 2, 3 UL or 1, 2, 3 ULL. That tells us that it's unsigned. It's unsigned, and either a long or a long. I don't think it really makes a whole lot of sense to put long and long in the same thing, because I don't even know if that's well defined. So I probably wouldn't do that. But yeah, with no suffix, the literal defaults to type int, which may lead to problems if you try to do a literal, which is like a very large integer that an int can't fit. Okay, so that's everything for integers. Much quicker than characters. Then we've got floating point. So floating point, when you think of floating point numbers, basically it's synonymous to decimal numbers. And by decimal, this time I mean with a point, decimal point. Maybe I should say decimal point numbers. So 6.2.5 floating point numbers, or floating point types. Just, yeah, aka numbers with a decimal point in them. Okay, so there are three. I guess something to mention. Because you can only really give a finite number of bits to anything you want to represent, any kind of data, a floating point type is always going to be an approximation of a real number, right? A real number meaning maybe it has a decimal point, maybe it has 1,000 decimal places. A real number in a fixed amount of memory. So especially if you think of a number where the decimal places is infinite, think of pi, for example, 3.1415, like that, and so on. It's not going to be possible for a computer to store the exact value of pi because there are infinite digits to keep track of. So rather, you can only, for example, if you're going to have 32 bits, for example, you can only be you can only be so accurate in trying to represent this particular number. So floating points are always going to be approximations of real numbers using a fixed number of bits. Now there are three types of floating point number. Or maybe it's better to say there's three floating point types. There's the float, which is basically single precision. There's the double, which is the double precision. Typically means you provide double the number of bits here than with the float. And the long double, which is extended precision. So possibly even more bits are given to the long double. And then the meaning, the number of bits that you actually give to each of these is implementation defined, but generally speaking, you'd expect it to increase as you go down. Okay, and floating point literals. 6.2.5.1 floating point literals. If you were to write, some random decimal number, like decimal point number, the default type is double, not float, interestingly enough, it's double. But the suffix f changes this to float, and the suffix l changes this to long double. So the inclusion of both a decimal point and the L suffix tells us to make it a long double. If there was no decimal point, it would just be an integer, so the suffix L would be a long integer. So it's the decimal point and the L that tells you it's a long double. There is also, you can also actually write things in scientific notation. You can have literals be written in scientific notation, something like if you have 3.0 times 10 to the power of 6, right? If you wanted that number in C++, you could write, I think, 3.0 E6, and that's how you would write that literal. So a combination of suffixes and this E for, I think, exponential notation is what that is, but I'm used to scientific notation. But these are the kind of ways you can sort of adapt or change your literals. Okay, and the last fundamental type that we talk about in this chapter, the last fundamental type is void. Uh, 6.2.7 apparently. Apparently I skipped 6.2.6. Let's see what that is in a second. Syntactically, void is a fundamental type. However, strangely enough, no objects or variables or anything can have a type void. Okay? Either, the only two sort of significant uses of void is specifies that a function returns nothing. So, if you've seen a bit of C++ or C code, you might have seen a function that looks a bit like this: void f, and then something else like this. This is again just a block of code, but this void here tells us that the function doesn't sort of send back any value. You might take in some stuff if there's arguments in here, if there's parameters in here. It might take in some stuff and do stuff with it, run some instructions, but it doesn't push back anything back to the caller. So that's what the void is there. Or it is used as the base type for a pointer. base type for a pointer. And we do talk about void pointers a little bit later in the chapter 7 for a pointer to objects with unknown type. So if there is an object and you don't know what the type is, if you were to take its address, that address would be void star, like it would be a pointer to a void type, because we don't know what the object, we don't know what type the object has. The object has a type. There's no object without a type, but with an unknown type, we would assign the void star pointer, the void star type to a pointer. Okay. So that's pretty much everything on the fundamental types. And the last bit that we will mention is the sizes of these fundamental types. So 6.2.8, sizes. So I've kind of fleetingly mentioned that, for example, a char typically has 8 bits, and maybe a double is bigger than a float, and a long double is bigger than a double, and maybe a long is bigger than a long, or things like that. That's the kind of impression that I've been trying to give. But in reality, the sizes of these things are implementation defined. The standard, the ISO standard, doesn't actually give a strict set of rules to adhere to. The actual rules that the standard gives are the following. So what the standard guarantees, what the ISO standard guarantees for whatever implementation you're using, 1 equals to char, is less than or equal to short, is less than or equal to int, is less than or equal to long, is less than or equal to long. So if we just consider this rule, what is this really saying? This is saying a char is going to be 1 byte, unit is byte here. A char is always going to be 1 byte, that is always true. But a short, you could argue, could technically equal a char, which equals 1. So this could also be 1. And this could also be 1. And this could also be 1. So this rule alone basically is saying you wouldn't expect, for example, long to be smaller than char, but they could be equal. So there's no real sense of long is actually big, has to be bigger than char in any way. The next rule is 1 is less than or equal to bool, is less than or equal to long. Again, like generally speaking, we think of bool as 1 byte because we don't need, there's only 2 things to think about, either it's true or false. But in reality, so long as it's less than or equal to long, we wouldn't be breaking any rules. Char less than or equal to w char t, less than or equal to long. Remember, the w char t is for the wide characters, so you probably expect it to be bigger than char, but not necessarily, right? The rules don't say that it has to be bigger than char as well. Float less than or equal to double, less than or equal to long double, right? Same kind of thing. And the only real strict rule is that for some type n, the unsigned version of that type and the signed version of that type, they're all equal to each other in terms of sizes. So like for a char, if we had an unsigned char, a signed char, and a regular char, they should all have the same number of bits associated to them. Same with ints, an unsigned int, a signed int, and a regular int, which is also a signed int, will all have the same size, and the same number of bits. So these are the real strict rules associated to them. Now there are additional rules, so in addition, a char is at least 8 bits. Okay? A short is at least 16 bits. It is only at this rule, it's only because of this rule, that a short cannot be the same as a char. It's only because of this rule we know that a short probably isn't going to be 1 byte. Because it's 16 bits and a byte is typically 8 bits. So in that sense, it's the only real reason why we expect short to generally be bigger than char. If not for this, we could have some really weird implementations where short and char are the same thing, same size, sorry. And a long has at least, oh, my writing's going to be really bad. A long is at least 32 bits. Right? But the word at least kind of still keeps things relatively vague. We're not saying it has to exactly equal 32 bits. We're not saying a long has to be 4 times bigger than a char. We're just saying that a long has to have at least 32 bits. And so long as you follow all these rules independently, you have a valid size. You have valid sizes for all your types. Now, there is a general chart that is given for typical implementations. So I'll just quickly point it out. And this chart is something that you can generally rely on, but always remember that for implementation-defined things, you can't guarantee stuff until you read documentation. So, you know, a char usually looks like, if this is 1 byte worth with a char, a bool is typically also 1 byte. A short is typically double that. 2, an integer, have I given myself enough space? Integer is usually 2 lots of a short. I might have to draw a bit smaller. A long is usually double an integer. Okay. A long, funnily enough, is usually the same as a long. I actually was a bit surprised about this. I was under the impression that a long was double long, but I checked this with some scrappy C++, and it turns out, yeah, they have the same size. Int star, so pointers, at least for I guess a 64-bit machine, typically the same size like this. Double is sort of like this, and gonna run out of space. But how clear is it? Double is this rectangle down here, and a long double would be double the double. It seems. Do a different color. I seem to have missed float in my chart, so I have to add that in. But I guess just to do this, imagine the long double is double the double. Got it. A long double is 2 times the amount of a double. There we go. And a float would be usually half. So float would be in here. I'm just being lazy now, but a float would be half the double. All right. So this is typical, but again, not strictly always the case. Things can be different for different implementations. All right, and there is 6.2.9, which is on memory alignment, and it is very cool. It's definitely very relevant to types, and it's something where it's very cool to learn about. But I also think that it's it's a sort of a topic with enough depth and detail in it, where I feel like it's better off being a different thing, being a completely separate thing to talk about. So I'm just going to leave it for now and come back to it when I feel a bit more comfortable with it. I think I skipped a chapter, 6.2.6 or something. I want to check what that is. Yeah. 6.2.6 is just a sum up of all the prefixes and suffixes we saw in the literals, so I wasn't too fussed about that. Okay, and just like that, we have finished 6.2. We finished the types part of types and declarations, which is good. Now it's time to look at the declarations part of this chapter. Now we kind of start to see how we use types in actual code a bit more. So 6.3, declarations. If you haven't taken a break yet, this would probably be probably a good place to stop. I think I've been going for about an hour and a half, so. Alright, so. I think the best way to start this is giving a nice sort of definition that's easy to follow. So a declaration is providing an identifier and specifying its type. Now, when you see the word identifier, when I use it, it's pretty much, I kind of use it interchangeably with name and label. Identifier is the most technically correct word, but name and label, I feel like I can get away with using those. So name, label, or identifier, pretty much all the same thing. And so we have to make sure we always specify a type for a particular identifier. And what identifiers are used for, it's a way of giving a name to data that we want to sort of remember in memory or represent in memory. Now, that's the definition of a declaration. We also have the actual word definition that we need to define in this context. So definition, as a technical word, means a type. It's a specific or a special type of declaration that also supplies all the information, it supplies all that is needed in a program to use the associated entity. So entity is a very broad word, but essentially, like I said, an identifier is used to label or used to identify something in memory. But if we want to use that thing in memory, there needs to be some relevant information in that memory associated with the data. So easiest way, I think, to talk about this is using examples. So for a variable, we need to a value needs to be provided. So provided. So a value for a function, we need an implementation, because we can actually give a function say what it returns, what return type it has, and what arguments it takes, and we can talk about that. But without actually saying what the block of code is that needs to run, that's just a declaration. It's only when we tell what instructions are associated with the function, that's when it becomes a definition. And then for structs, it's a bit more specific. Structs, you might talk about the properties. So again, a struct, I guess, a quick definition of struct, you can think of as a bucket type, which is able to store sort of multiple of other types. So as an example, typical example is like a coordinate struct, which has like two integer values associated. So like struct coordinate, that's the name, that's the identifier, and then you might say int x and int y. So it's like a container type which contains these two other sort of subtypes. It's like a composite type which can contain various other types within it. So if I just said struct coordinate, that would be saying the type is a struct and also giving the identifier. But it's only when I give the actual thing, the actual composite type, the actual like sort of primitive types that are within it, that's when this is a definition, right? So for structs, giving the properties, these values in here are the properties. All right, now a very specific rule. There must exist exactly one definition for each identifier, and hopefully this is something that makes sense. But essentially, you got to remember that you want to make the compiler's translation job really like as easy as it can be, right? You want to be able to make sure things are clear and unambiguous. If you have two definitions of the same name, right? So you declare an x, and then give it a value like 3. That's like a variable that you've defined. And then you redefine it, that is, you make another definition with a different value. If you then ask the compiler, like, oh, I want to now print x, I want to show the value of x now, could you do it for me? The compiler is going to, throw its hands up and I'll say, well, I don't know which x you want, right? This is very ambiguous. I'm not sure what you want. So this isn't allowed, right? Giving the same name two separate definitions, two separate values, and two separate definitions is a problem. However, this is a bit more of an interesting rule. However, you can have many declarations. And I feel like there will be people who hear that and think, I'm pretty sure that's wrong. Because I feel like I've tried to declare the same thing multiple times and I've come up with an error. And if, for example, you've tried something like this, where you have int x, you'd be right. You'd say, well, I've tried to run this kind of code before where I've just put int x and int x again, and I've come up with it's come with an error. But if you look at the error closely, you'll see that it's a redefinition error. It's a redefinition error. Definition error. Not a redeclaration error. Right? And you might think, oh, well, it's still called an error, and this is clearly a declaration. We'll talk about that in a second. But on the flip side, if you try to declare a function, the same function over and over again, if you try to declare a function like int f, like that, right? This is just a declaration because I didn't give any implementation. And you do that 10 times, right? I don't know, 4. If you do that as many times as you want, the compiler's not going to have a problem with that because you're kind of just doing the same. There's no real ambiguity yet because there's no different definitions across the different declarations. It's just the same thing over and over again. So the compiler can interpret that, can translate that no problem, right? So there is definitely evidence for you being able to have as many declarations as you want. And the question becomes, well, then how come I can't just declare as many integers as I want? What's the difference between declaring all these functions versus declaring integers? Okay, and that's where we get into something called implicit definitions. This idea of implicit definitions. So there are certain sort of objects, generally, certain variables and things like that, where if no definition is provided during declaration, a definition is sort of done implicitly. So without the coder or the programmer actually telling it to do it, providing a particular definition, a definition is just sort of done by the compiler. So when you write int x, you might think, oh, I've just declared the x. I haven't actually defined it yet. But in reality, without a definition given, in this case, an implicit definition will be done. So I believe the exact behavior of what the implicit definition is implementation defined. So sometimes it'll default to 0. I think I've had an instance where it wasn't 0, but we can imagine for now this x might just be given the value of 0, just as a definition, as an implicit definition. So when you do this again, you might think, oh, I've just declared it twice, surely that's allowed. But in reality, you're doing another implicit definition. And we're not allowed to have more than one definition for a particular identifier. if you're going to use the same identifier, you can only declare it. You can't redefine it, and you are redefining it because of implicit definitions. And that's why you get a redefinition error when you do this, rather than a redeclaration error. All right. So that's kind of some of the rules or sort of points about declarations. We now look at them. We now look at declaration a bit more formally. Okay. 6.3.1. The structure of declarations. So a declaration can consist of 5 parts. So you have optional, prefix specifiers. For example, there's static and virtual. We have the base type, which we always need, as by definition. We have the identifier, which is again generally needed. We can have optional, suffix, function specifiers, for example, const and no except. And you can have optional initializers, which is basically what turns what turns a declaration into a definition. So initializer or a function body for functions. Function body. Okay, so as an example declaration, we have const char. We have star kings, these little brackets, equals, and then it's a list of strings. And okay, so we have to break down this particular example into the different types. We have to break it down into different parts. The const char part is the base type. Right, we kind of skipped the prefix part. The declarator or identifier. I should say declarator. That's the wrong word. Identifier is part of the declarator, but there's more bits to the declarator. Sorry, so it's base type and then declarator, not identifier. Put the wrong thing in. Yeah, this entire part here is declarator, and this part here is the initializer. So we have no optional suffix function specifier, and we have no prefix specifiers either, but these are the 3 parts that we have used. Yeah, it's getting annoying. That says initializer. Okay, so the declarator, if you look at the declarator in a bit more detail, the declarator consists of the name or identifier plus possibly some declarator operators. Declarator operators. This is some. So we'll just go through the list of these because I think it's good to see them. So you have a table that's like prefix, star, pointer. So this is basically, is a prefix or a postfix. You got the symbol, you got like the meaning. You got this one, you got prefix star const, which means constant pointer. You got prefix ampersand. In this case, it's an Lvalue reference, which is new, but you see it in chapter 7. Same with prefix, the symbol ampersand, ampersand. It's an Rvalue reference. Prefix auto is a function using the suffix return type. To be honest, I don't know if I've ever used auto as a declarator operator. I've used auto before. I'm not sure if I've used it as a declarator operator or if it was something else. It's kind of used more as a base type, I feel. Postfix symbol is this. We saw this in the King's example, and this means it's an array, right? Arrays being a list of object of the same type. Postfix, we have parentheses, that tells us the function. There's also this arrow thing. I haven't seen this one yet, so I'm not sure what it is, but if you have an arrow, means returns from function. I've never seen that used in declaration before, so I'm not too sure about that one. But everything else, especially the last two, I would say, are things that you can add to your identifier to make sort of a slightly different object. So, you know, for function, for example, I talked about if you want to declare a function, you might give it a type, and then you give a name, and then adding these parentheses is what tells the compiler that this what we're declaring here is a function, not a variable. So we have a type in the front, but it's those parentheses that tells us it's a function. Same with array. If you have int a, you put brackets, this tells us that this isn't just an integer, it's an array of integers, or a list of integers. So these are just some things to know, to try to recognize, and hopefully get used to over time. And just something in terms of order of operations. Generally speaking, postfix operators are applied before prefix operators, unless you use brackets. So, you know, think of BODMAS as like order of operations. Now that we have new operators, we need to define a correct order to do things in. So if you had char star kings brackets, this means an array of pointers to chars. So again, have to be a little bit comfortable with pointers here, but what we're saying is this is not a pointer to an array. This is an array of pointers of type char star. Yeah? Versus, if I was to explicitly put brackets, char kings with the pointer, and then put the brackets. Now I've explicitly said I want the star to be applied to the kings first, and then do the postfix. Then this means pointer to an array of chars. So we say kings is a pointer, which then points to an array that contains chars in it. So the interpretation will change, but generally speaking, we do the postfix first and then the prefix. All right. How's this? Oh wow. Okay. So trying to, if you ever try to declare multiple names, you might see syntax where you try to do multiple declarations, like the declaration of multiple names in one line. So one declaration has multiple names or identifiers. So, for example, you might say something like int x y with a comma between and then a semicolon. This is equivalent to doing int x and then int y. So the base type basically gets sent to both x and y. If we had int star p y, so we're saying, trying to use a pointer here, the pointer operator only gets applied to the p. So declarator operators only get applied to the single name that it's next to. So we have int style p, but we only have int y. Only the base type gets spread across. The operator stays just with the p. And so similarly, if we have int x and star q, then we have, that's the same thing as int x and int star q. That might be a bit more obvious to people because the star is only on the q. And then finally, int v10, which basically means array of size 10, versus star p, is the same thing as saying int v10. Again, the postfix in this case, the operator here, is only applied to the one name that it's next to. And then int star p, again, this star is only applied to the one name that it's next to. So operators, array operator, pointer operator, whatever operator, is only applies to the individual name, and the base type goes to all the names. Okay. Now we have rules for names. There is a few. I should have mentioned actually. Generally speaking, it's only really good. Like the ones down here aren't considered great practice because readability isn't amazing, especially with that operator rule. So generally, we avoid this kind of notation. The top one's usually the only one that's kind of okay. Even then, you wouldn't want to do it for like a lot of variables at once, a lot of names at once. Right. So 6.3.3, names in general. So what are the rules for identifiers? Right, so the first char must be a letter or an underscore. C++ keywords cannot be used as a name. So what is a keyword? You can think of things like int, char, so the base types that we've looked at. There's other things like if, else, while, for. Those are, again, keywords that you'll see constantly throughout C++ code. Basically, yeah, those keywords you cannot use as a name because the compiler will get confused. We don't want to confuse our compiler. And then, in general, only letters, English letters, numbers, and underscores are allowed at any point in the name. So if you try to use a full stop, try to use a star, an asterisk, try to use an ampersand, it's going to cause problems. Again, because a lot of those symbols are operators, so the compiler is going to get confused between are you talking about the operator or are you talking about the name? So that's why just blanket statement, just only allow letters, numbers, and underscores. The only real thing of convention that's important to know is maintain a consistent naming style for everything. So typical conventions are capitalize names of user-defined types. So if you define, for example, a class or a struct, capitalize the name of that type. Start names of non-type entities with lowercase. and prefer snake case over camel case. So these are all things I've lifted from the book, and they're all preference based, right? So you might find people who do camel case and not do snake case, or you might find people who don't capitalize their user-defined types, which would actually be very weird, but it's fine. But there are definitely points of contention with anyone's style guide. But the only rule that is universally agreed upon is that consistency is king, right? So regardless of what happens, especially if you're working on someone else's code base, you want to try and adapt to their style, what's currently been used so far, rather than sort of adopting your own thing and then having clashes. Okay, so continuing on, we start to look at scope, right? So before we sort of get into the details of that, I think a good way to start is by introducing this word block, a block of code. A block of code. I think for C++, the best way to talk about this is you'll see a lot of curly braces like this. Essentially, every pair of these you can think of as the beginning and end as of a block of code. So like a block of code starts with an opening of one of these, and then ends when this with a closing braces. So easy example, if you have a function like int f like this, the block starts and then ends with the closing bracket. So in general, I'm going to talk about blocks of code, I think, a lot when I do talk about this. So just bear that in mind. It's just the opening and closing brackets, squiggly brackets. All right. So now we talk about different types of scope. So when we declare something, a declaration introduces a name into a particular scope. The name that's been declared can only be used within that scope. And in general, I would say, if you think about a particular block of code, right, so that with those squiggles, the scope of a name begins where that name gets declared. So if that name sort of got declared here, for example, int x, and the scope, so the scope of x in this case starts here and ends when the block it was declared in finishes. So if we have a declaration here, I'll write it bigger. If we have a declaration here, the scope of this variable, in this case, exists until the block completes. That's the general thing I would say. That's kind of the general rule. So I think the best, and then the next thing to talk about is the types of scope you can have. So I think there's a fair few, but I think I'll mainly look at start with function scope, especially because we were talking about functions just now. Function scope. So the way function scope works is basically a name is in scope from its point of declaration. That says declaration, sorry. Until the end of the function. So you have some function and you've declared a variable inside, or you declared a name inside that function, and that's the scope exists from that declaration till the end of the function, till the return statement. And have a note here, parameters, basically the data that a function takes in, count as being within the function scope. So for example, just Just again, if we have some int and there's a function, so we have a function f that returns an integer, and it takes in, let's say, a character c, and we declare another integer x. We would say both the character c and the integer x exist within the function scope, right? And we can basically use c anywhere in the function, right? Because it's brought in. X we could use anywhere from the declaration point down. So not before we declare it, we can't use it here. Can't use it before we declare the x, but afterwards that x is within the scope. But then once we reach the end of the block, we can't use x anymore, right? Using x down here isn't allowed because x was declared in here, right? So once the block ends, x is no longer accessible, we say. And same with the character c. So that's function scope. Next one I would do is with class scope. Class scope is very similar in the sense that anything declared within the class can be used within the class after the declaration point. If you're not super comfortable with classes, that's all good. For now, just think of them as class scope. For now, just think of them as something you can kind of create a bit like a function. In fact, I don't even know if I know the syntax very well. I think it's something like this. Class A, for example. I don't think there's any brackets. So you might have something that looks a bit like this, right? And visually, at least, it looks a bit like a function. You know, you have a return type here and a name. In this case, I think we have the word class and then an A. And then again, you have a block, right, with the brackets. And then you might have another variable that you define in here. Again, that x is accessible anywhere within this block, but then isn't accessible anywhere outside. So I guess in terms of writing, so any name declared in a class, but outside any function in a class, just in case you have a class in the class, enum class, which is like something else you can kind of create, or say other namespace, which is a sort of word that we will introduce at some point. But essentially, you can create, for example, you can make a function here, int f. You can have sort of inner blocks within the outer block. But in terms of having class scope, you want to declare it within the class block, but not within sort of inner blocks like this function. If we put the x in here instead, then this x would have function scope, but not the entire class scope. In fact, this x here would be accessible within the class in its entirety, so therefore would be accessible within the function as well, because it's outside the function scope and inside the class scope. So, so any other, if we want to be in the class scope, you have to be declared in this class block, but not within these inner blocks, such as functions, enum classes, other things that you can kind of create within the class, other blocks you can create. Class scope. We'll do statement scope. Again, I guess strictly, I don't think we've actually talked about things like if statements and stuff, but assuming you have a different language under your belt, another language under your belt, that shouldn't be too much of a big deal. Essentially, any especially variables in particular, but any name, I should say, just to be generic, any names declared within an if, else, while, for, or switch statement has statement scope. So I think the easiest way to look at this is with for loops, because you can actually create, you can actually declare variables within the brackets. So what I mean by that is you might have something like for int I equals 0, I less than 10, plus plus I, which is basically going to iterate through the values 0 through 9, in this case, because less than 10. 0 through 9 and assign that value to I. And then we're going to start our block. Hit. And you might create something else, int x for example, declare that. So both I and x have statement scope because they're both accessible within the for loop block, right? This is in this block. This I is, you can access I anywhere within this block. X you can access after the declaration anywhere in this block, right? So anywhere here, sort of thing. So that's what statement scope is. Again, this idea of having a block, you're accessible within the block, but then that I or that X, for example, isn't accessible outside the block, here or here. So that's statement scope. And the last one I probably do is global scope. The global scope is the one that's a bit of an exception in the sense that you don't necessarily have a visible block, so to speak, with brackets. So global scope, and that's essentially any name declared within a file, but outside any block. So you might have some function, like you might have your main function, int main, like this, and return 0, for example. Right, very typical boilerplate. You might have some other function, int f. You might have a class C, and it goes like this. So you have these different blocks, but all of these, and let's say all of these are contained within the one file. If you also create an int, let's say z, like that, within the same file, but outside any of these blocks, then this z has global scope. That is, it can be globally accessed within the file. The function main, the function f, the class C, all can access z because it is within the same file and it's outside any particular block. So it's kind of like, if you think about it in a diagram, imagine this represents like your entire scope, I suppose, your global scope. Main has a scope like this. F has a scope like this. C has a scope like this. So this is main F, function F, and class C. Anything declared in main can be used in main, but can't be used anywhere else. Anything declared in F can be used in F, but not anywhere else. Anything declared in C can be used in C, but not anywhere else. Anything declared in that global scope can be used anywhere else in the global scope, but can also be used in any of these inner blocks. So outer names are accessible generally within inner blocks, as well as the block it was declared in, the global scope in this case. Okay, so that's the general rule. There's a couple others. There's namespace scope and there's local scope. Local scope generally refers to like anything that's not global scope, but in this particular book, he defines local scope to be basically the combination of function scope and something called lambda, the scope of functions in lambda. But we haven't really looked at lambdas, so I think we'll skip that. Namespace scope, we haven't really looked at namespaces yet, but essentially you can think of it kind of like how classes, you'll sort of introduce a block and declare things. Namespaces are another thing you can create in a similar way. But we haven't looked at namespaces, so I wouldn't be too worried about that just yet. Now, there's this idea of scope hiding. Scope hiding. Imagine that you declare a name in an inner block that has an identical name to something in an outer block, or an outer scope, I should say, in a scope, and an outer scope. Right, so we think about that diagram from before. Typical example is, let's say this is your file, right, or your C++ file. In the global scope, you might produce int x equals 5, and then you might create your main function like int main, and then do something like this. And then you might say int x equals 0, and then you request to the you make a request to print x, right? And then you return 0, for example, or whatever. And then, you know, generally we said the compiler, if you have something like this, it's unlegible. That's this. But this line basically printing x. If you're not comfortable with that, yeah, that's alright. I should write it bigger. Int x equals 0, and then this one x. Yep. Is that any better? That says stdcout with 2 dots in between, 2 colons in between. Sorry. Anyway, you might ask, well, is the before we said if we kind of did this kind of thing, where we have x's twice, the compiler might get confused, like which x do you want me to print, right? Isn't this, you know, you could argue that this is kind of a redefinition problem, because we've got the same name twice with two different definitions. But because of this idea of scope, the compiler is told to prioritize, so the compiler prioritizes the inner scope, or the inner block, right? So if it's asked to print x, it first looks in the inner block. Because there is only one x in the inner block, it will use that x, no problem, right? It'd be problematic if we had 2 x's, like int x equals 3. If we had 2 x's in the inner block, then by the time we did this, we'd have a problem. And that would be a redefinition error. But because we have one in the inner block and one in the outer, in the global scope, we have one in the function scope and one in the global scope, it just picks the one in the function scope. So this is the idea of scope hiding. Essentially, this x here is hiding the outer x. It's not really seen by the compiler because it just prioritizes the first one. So this is the idea of scope hiding. There is something called the scope resolution operator. So the scope resolution operator, in essence, it's operator. In essence, it specifies which scope you want. So it looks like this, so 2 colons. And it basically specifies which scope you want. So if, for example, you were to put these 2 colons and then put some name, right, like x, for example, or whatever, this would indicate the global scope. Right, so 2 colons and the name would indicate global scope. I want global scope. So in this case, if I was to put, I believe, colon x, like that, right? So that says colon x instead of just x. The compiler would know not to look inside the function, but instead look outside in the global scope, and so that would print 5 instead of 0. You can also put either like a class name and then colon name, and that will tell the compiler to look within the scope of that particular class that you specify. Same thing with namespace. With that name, you can do that. I don't believe it works with functions. Yeah, it doesn't work with functions, and I don't think it works with statements either, because statements, you can't really give them a label, I suppose, and functions, it doesn't work with that either. So, for example, sometimes you can actually just put in artificial blocks as well, like without giving them any particular label. Like it's not necessarily a function or anything; it's just a block. So, for example, if you have something like int f, like this, and you say int x equals 0, and then you have another block, like you can just put in a block without really putting anything else. You just put some squiggly brackets in here, right? So it's the same function, just within a particular block. You say int x equals 5, and then you print x. I'm not going to bother writing the whole thing. I'm just going to say print x. That's wrong technically, but it's alright. right? Again, the compiler is not going to be confused because you've actually created a kind of artificial inner scope within this function, and so it's going to just choose this one. It's going to prioritize the inner scope. That's fine, but there's no way to actually access this guy here, right? Like sort of zooming out of us into a scope that isn't a global scope or isn't a separate class scope or a separate namespace scope. Zooming out in this way isn't possible. You can't access this x equals 0 if you're going to be within this in the scope. So just this isn't. I'm not really sure when you would actually use like an artificial scope like this or an artificial block, but the general rule is there is no way to use a hidden sort of function declared name would be the thing that I would keep in mind. All right. So next bit. So that's everything to do with scope. To understand about scope in terms of scope is generally very a conceptual thing rather than a C++ specific thing. The resolution operator is specific to C++, but generally speaking, scope is something that you'd have to understand across just about any language. Pretty much the same rules each time. Next thing to talk about is 3.5, which is initialization. Initialization. This idea of giving a newly declared, typically with some variables, giving it its first value, right? Giving a variable a value in general is called assignment. This idea of assigning a value, but you can always assign anything. You can always assign a value to a variable. Either you're assigning it or maybe you're reassigning it, but in both senses it's assignment. But initialization is this idea of the initial value you give to the variable, the first value you give. So there's actually a few methods or like syntax methods to like different ways of initializing. So I'll just say, for some type x, for some type capital X, right? You can have like x a1 and then put little squiggly brackets. In this case, this is not a block. This is something separate now. Put like some value v in here. X a2. You can say equals and then squiggly brackets and put the v in there. X a3 equals v and x a4 and then parentheses. Oh, sorry, parentheses v, not 4. Parentheses 4. And then semicolons. So the one that people will probably be most comfortable with if they haven't really seen C++ before is this one, which is fair enough. This fourth one, I'll be honest, I don't even know if I understood that at all. I might have to reread the book, but I don't know, it wasn't really looked at in my notes at least, so we might not talk about it much. The one that's a bit more interesting is the very first one. And to give it a kind of a brief introduction, this is called list initialization. List initialization, you're kind of initializing using a kind of list-looking thing with the brackets. And the important thing to note is it does not allow narrowing, and we'll talk about what that means, I think, right now. Now, it says here that basically this can be used, from a technical perspective, this can be used in any context, the first method, but it was only introduced in C++ 11, which is why it's in this book, but it's also why a lot of people might be more comfortable with this. Even old C++ programmers probably took a while to sort of go from this to this, because this was kind of the norm, and this was kind of newly introduced for C++ 11. Okay, so now we'll talk about list initialization in a bit more detail. So yeah, it does not allow narrowing. So I think the easiest way to explain narrowing at the start is basically just giving a couple of examples. Or maybe I'll give a brief definition first. So a value which requires a large number of bits will not, maybe I should say a value of a type. So a value of a particular type that requires a large number of bits will not be assigned to a variable of a type that provides, I guess, a smaller number of bits. That's how I would probably describe it. So this idea of like, if you have a large value, you can't narrow that value, and by narrow I mean the amount of space it takes in bits. You can't narrow that value to make it fit into a variable of a type that only allows for a smaller number of bits. So now I think, examples would probably be helpful. So assigning an int to a char is not allowed. We think about that section on sizes. Generally speaking, integers are going to be bigger than chars. So if you were to write something like int x and then braces, this is that first method, right? This is a list of initialization, and you were to try this. Sorry, wrong way around. Assigning an int to a char. So you have a char and you're assigning an int to it. This is going to be problematic. Using sort of the conventional sizes, this will take up 32 bits, right? Generally speaking, this will take up 8 bits. So technically, char can store a value between, let's say for unsigned char, generally speaking, char will happily store anything from 0 to 255, right? As we said for unsigned. So it can happily store 4. Like it can do that in 8 bits. That's not a problem. But what list initialization says is, if the type of the value takes up more bits than the type of the variable allows for, then this isn't going to happen. We're not going to let this happen, right? Having said that, we're allowed to go the other way around. So if I said int x and then put a char in here, this is all good. So this causes an error. This is a narrowing error. In this case, you're trying to fit 8 bits. You're trying to fit 8 bits worth of stuff into a 32-bit sort of entity, which is completely fine. You've got something that's 8 bits. You're trying to fit it into something that's 4 times the amount, for example. Pretend that's 4 times the amount. It's going to do that no problem. That's widening, not narrowing. That's fine. But going from something that's large and trying to squeeze it into something that's small is going to be problematic. So another example is if you had trying to fit, I think, a double to a float, right? Again, usually double is double the number of bits. So if I had 4.6, right? Because generally speaking, literals, right? Literal decimal point numbers default to doubles. And then I said, okay, float f or whatever, and we tried that. I can't remember the exact, I believe it's generally 32 and 64. So you're trying to fit 64 bits worth of information into a 32-bit object or entity, so that's going to cause problems. That's going to cause a narrowing error. But again, going the other way around is, if anything, a widening thing, and that's perfectly fine. So list initialization will sort of look for that narrowing and make sure it doesn't happen. And the reason why that's advantageous a lot of the time is you don't have this issue, you can't have this issue where you accidentally lose information. Sometimes you might think that, sorry. sometimes you might think that, it's not a big deal, especially in that, char c equals 4, because the char will fit the 4. But generally speaking, you don't want to put yourself in a position where you're sort of removing bits, shoving off bits just to make things fit. So as a blanket statement, list initialization is safer. It's a safer way of doing initialization. That's to contrast it, I guess, with the regular, like the equal sign initialization. If you were to do something like, what's a normal example? Like, I think int x equals 4 point. Yeah, let's just do that for now. In this case, I mean, I feel like most people know what this behavior is once they kind of get comfortable, and sometimes it's even helpful. But just as an example, if you were to do int x equals 4.7, this side is a double, this side is an integer. If you use the equal sign here, what will happen is this double will basically get converted into an integer and essentially rounds down every time. So 4.7 will round down to 4, and that value will be assigned to the x. With the list initialization, it will basically throw an error saying that you're narrowing from 64 bits to 32 bits. I wonder what happens if you try to fit a float into the x, because floats are generally the same size as ints. So I'm not too sure. I might check that. But yeah, with an equal sign, that narrowing check isn't done, so you're going to end up losing information. You will lose that 0.7, which sometimes people are happy to do, especially if you want some rounding down for whatever reason, but it's something to bear in mind. But generally speaking, that list initialization, because it is safer, is preferred these days, at least with C++11. Now, when using auto, and we'll talk about the keyword auto later in a second, when using auto, there is one sort of issue when using list initialization. I guess I should give a quick sort of intro into what auto is. Auto is basically a way of declaring a variable, but instead of specifying its type, use the keyword auto, and that basically tells the compiler to figure out what the type should be based on what you initialize it in terms of its variable. So, for example, if you were to say auto x equals 3 with the equal sign, the compiler would look at this and say, well, you're giving it the value 3, so I'm pretty sure auto should be int, right? Like this type here should be int, x should have the type int. So in that sense, auto is kind of a way of implying or inferring what the type should be based on what value you give. However, if you were to do auto x parentheses 3, which is what is sort of, this would be preferred if this said int, right? If this said int, this is what you'd do. But because it's auto, what the type that is inferred by the compiler, right? Here the inferred type was int, as expected. Here, the inferred type is not int, but rather it is Initialiser List. With a sort of specified type of int. It's an Initialiser List, that is a list given at initialization. Okay. It's an Initialiser List, meaning that it is a list given at initialization time with int elements inside. That's the kind of inferred type that is given, which is likely not what people want when they do a line like this. More likely they were just trying to give the value 3 to x, but auto got a bit confused. So the general sort of rule of thumb, prefer equal sign for initialization when using the keyword auto. Alright. There is something called the empty initializer. Sometimes you just want to give it a default value. So the empty initializer. So you might say something like int x, and then you give the brackets, squiggly brackets, without actually giving any value inside. This is used, the empty initializer is used to indicate that a default value is required. And usually those default values are zero-like. They are like zeros in some way. For example, in this case, for integers, you'd have defaulting to 0, and then generally you have 0, 0.0 for doubles, null pointer for pointers, the null pointer. You can have empty strings if you're trying to initialize a string with the empty initializer, empty strings. And you have something, and you have an empty vector. Again, I'm not sure, I can't really remember if we've talked about vectors at all yet. It is introduced a lot more detail later in the standard library sections. But think of vectors like arrays for now, like really cool arrays. But yeah, so if you try to initialize a vector with the empty initializer, you get an empty vector, an empty array, so to speak, and then empty strings, null pointers for pointers. If you try to initialize a pointer with the empty initializer, 0.0 for double, 0 for ints. I'll talk about that later. Yep. Okay. So from there we have 6 point. Oh, we have an actual thing. We have an actual heading. You can also sort of not provide an initializer at all you declare. We've talked about this already a little bit, but so 6.3.5.1, which is missing initializers. You know, since you're declaring and not giving any particular value. So this is the context when you choose to leave out an initializer, basically not provide any value. You know, I think we've seen that generally you get some kind of, sometimes you get implicit defining. I think on my machine, it will just give a garbage value, where if I say int x, for example, the compiler will say, okay, we need to give some memory to the x, that's something we have to do, but without any value, you just give whatever address, and if there was any value in that address before from some other program, it might just get assigned to the x value without too much drama. So there's an implicit definition there, you're giving some kind of value, giving something for the x to work with, but it's not something you kind of explicitly gave, it's sort of separate. But yeah, so sometimes you get implicit stuff like that. And in terms of practice, the only time to do this, like the only time to use a missing initializer, sorry, is if you are declaring a large input buffer, some kind of structure where you're going to take in a lot of data. Think about a large array, basically. Like, if I have some character buffer, and I give it an initial size of like 1024, right? What is this doing? This is allocating enough memory to store 1024 characters, right? So generally 1024 bytes are being allocated for this buffer array. And then, you know, when you do this, you might take in standard input or something and store it into here. That's fine. But if we kind of gave values to this, if we said, you know, please I don't know, make them all zeros or something, within this array. That's 1,024 assignments of zeros throughout the array. So I guess just to draw it out, when we do this part, all we're doing is allocating the space, which is saying this is our array. If you then do this part, then you have to then go back in and make every single one of these zeros, right? Which is extra stuff you have to do. It's extra instruction, and that's not a huge deal if it's just one value, if it's just int x or whatever, or even if it's a small array. If it's 5 elements, it's not a problem. But for large input buffers or larger buffers that have to sort of take in a lot of stuff and store it, this might be annoying. So that's kind of the only time where it makes sense to not provide an initializer, just sort of focus on allocating the memory. I should say, there's this idea of static objects. Static objects, including things like global, namespace, local static, or just normal static, members, like names, member objects, basically names, are initialized to the empty initializer value, the default value, if no initializer is provided. So if you make an object static, and I believe, again, the idea of a static object is talked about more later. Oh, it's not very legible. That says global, namespace, local static, or static member objects are initialized to the default value, the empty initializer, if no initializer is provided. Yeah, essentially, this idea of a static object, which we'll talk about more in a different chapter, I believe. Okay, yeah. We'll talk about it more later, but essentially there's this idea of certain objects, these static objects, will be initialized to the default value. Now, non-static objects, I believe that's what this is talking about. Local variables, so things declared in functions mainly, that aren't specified to be static, and heap objects, so objects created on the heap, which is a sort of specific type of memory, are not initialized without an initializer, unless they have an associated default constructor, which is mainly relevant to user-defined types. And apparently here, this is talked about more, default constructors, I talked about more in chapter 17, which will be a little while away. But essentially, in general, for now, just think, if you've got local variables like int x that you just created within a function, they're not going to be initialized if you do not, they're not going to be initialized to the default value if you do not give them an initial value. They will simply just be allocated to memory, and I believe that garbage value behavior happens. It just, whatever was there before, it will use it again. Yeah, so in generally speaking, if you're going to initialize a local variable, unless you're using the word auto, use the list initialization technique. Okay, so we've talked about initializing mainly, like, I've been working with integers a lot, right? This idea of, int v, int x, and then put the squiggly lines, squiggly brackets, and put some value. But what if you want to initialize a list? Or initialize an array, I should say. Initialiser Lists. So far we have considered no provided initializer or one initializer value. So we've considered so far no initializer, right? The missing initializer, and one value initialization, like for ints or for chars or whatever. For more complicated objects, we might need more than one value. This is primarily handled by Initialiser Lists delimited by the braces. So for more than one value, e.g. arrays, we use Initialiser Lists. It says initializer, sorry. Delimited, or like bounded by these squiggly brackets. So if I have int a, and then say 1, 2, essentially we are saying that this array A, this array A should be given the value of sort of element 1, element 2. And I haven't specified the size here, but the idea is the size can be inferred by the initializer value. So the size of array A is inferred by the compiler to be 2. If I have some struct s, right, then I can declare a value. I'll say lowercase t equals, and then 1 and some name, which is a string, right? And this is based on the idea if we created a struct before, struct s, which had sort of an int value and a string value associated with it, right? I'm not sure if I talked about structs as well, but basically, structs you can kind of it's a kind of a bucket or container that includes sort of other data types within it or other variables within it. So in this case, we're going to create an instance of this struct, which we call lowercase t, and its x value is going to be 1, and its name value is going to be capital N, name, right? So that's how we initialize structs using this list initialization. We can also do vectors, right, which we said before is kind of like just kind of like an array, but it's very similar to an array in this case. We say vector double, so we're saying we want a vector, but its elements should be of type double, and then you might put in some values like this. Right, so same kind of thing as before. Okay, so that's how we can initialize stuff with multiple elements. Notice how I use an equal sign. I'm not sure if you actually need an equal sign. The notes say that you can use one. I don't think it makes a difference if you include one or don't. But for now, you can put the equal sign. I don't think it makes a difference. But that's kind of like the method 3, I guess, of initializations out of the 4. I'll go get the titles. Alright, so now we have 6.3.6, where we talk about deducing types. Deducing types, specifically talking about order, and something called declarated type or something. DECL, and then type with little parentheses on the end. So, how would I describe order? We talked about it a little bit already, but in essence, deduces the type of an entity from its initializer. Plus provided sort of value. The type can can be a variable const or const expression. Const expression. Oh, const expression. In the sense that we can sort of further specify whether it's, whether it should just be a const or a const expression, as well as being an integer or a char or whatever. Now, the other thing, I think I should just specify that order requires the declaration of a variable, right? When you say order x equals 4, or order x equals character C, and then this type can be specified for that variable. Sometimes you don't really want to use a variable. It's not like we're trying to deduce the type of a new declared variable. We actually just want to know the type of a particular expression that already exists. That says expr for expression. We would write the whole word. So you plug in. You can think of it. You can think of. I say declaration type, but it's kind of abbreviated, so I'm going to use the first 4 letters of declaration. But yeah, declaration type, you can think of it, I don't need blue, what am I doing? Declaration type you can think of as a function capable of deducing the type of an input expression. So declaration type takes in some expression and returns essentially what type that expression has. So simple initializers. That's fine, yeah. So generally, for both of these, reports the type of an expression already known by the compiler. So in both these cases, it's not like during runtime the types are figured out. It's more that these deductions are done during compilation time. So when the compiler is doing this translation, it's figuring out what this value is, what the declarator type of this expression is. And when it sees order, it figures out what the type should be and almost replaces order with that type before it continues on. All right. Oh no. All right. So if we sort of delve further into order, in terms of when to use order, it's I guess it's sort of easy to try and fall for this convenience of just using order absolutely everywhere. Integers and characters and all the primitive types just use order the whole time. Which is sort of, a plan. 6.3.6.1, the order type specifier. So yeah, it's easy to sort of think, okay, well surely we can choose it wherever, but generally speaking, it's recommended to use it for complex types when determining the exact use it for more complex types when determining the exact type as a human is tricky. So, you might have, what's a good example of this? You might have a function that returns something really complicated. For example, maybe a bit too complicated. But let's say you have a hash table. Yeah. Let's say that hash table what a hash table is, just in case that's not clear, is it basically, it's similar to a dictionary in Python, if that's helpful. Otherwise, think of it as almost a function, but not really. Like, I'm abstracting a little bit, but think of it as a function that takes in a key and spits out a value. So, you might have a hash table that links numbers to colors or something. Yeah, that's not bad actually. Think of hex codes. So like all RGB codes. Maybe hex is better. I don't know anything about hex codes. But like, for example, if you plug in this key value, I think 0000, I think that spits out black, right? So like that, like hash table can kind of take in a key value, like the input value, and then like F. There's like hex codes, I think. It would spit out white, and then there's like ones in between, or whatever. So hash table like that. If you were to make a function like that, you might have to write a type. The return type might be something like hash table. I'm making it up, but like hash table. But then you also probably have to specify the type of the keys and the values. And in this case, it might just be string and string. But imagine if the value was an array or a vector, and that vector was of type, had elements of type double, right? Then you have this. But what if it wasn't doubles? What if it was a vector with elements of type some class, right? Where and that class needs to take in types as well, like int, whatever. And then you got all this stuff, and that's your thing. That's your type. And you're trying to create that hash table, right? And maybe there's some function that does something, some function f, and it returns x, where x is of that type. If I was to use this function, I was making some variable. This isn't within the function anymore. If I was to make some variable like my hash table equals f, I personally, normally I have to put the type of the variable here, but I don't really want to have to type this more than once. Even having to type it once is annoying, So that's where auto becomes clean, because what happens here is the compiler will basically check what the return type of f is, and then substitute auto for that. So the compiler does it for you, and that's fine. It's a translation, it's part of the translation process. Rather than you having to have that, in a lot of, especially if you have to call this function multiple times and capture the result multiple times, having to write this out a bunch of times to get the value out is annoying. So that's why I'm having to sort of hide away the complex types, not having to type them out all the time. That's a big use of the word auto, right? So, yeah. So auto is all about trying to not have to type not have to sort of explicitly write out the really complex types that can exist sometimes. It's also sort of good practice to use auto on small scopes, so small blocks of code. If you're going to use it on large blocks, when you've got large blocks, it can be kind of unclear because if it's in an outer scope, like the global scope, for example, you would expect that variable in the global scope is going to be used throughout the code, in different places. So not knowing its type because it says type auto at the top can be kind of annoying. So generally speaking, just have the type explicitly written in the global scopes or larger scopes, but using auto in small scopes is a good idea for complex types, because if it's not a complex type, it's not really much point. And something to mention, the type of an expression is never a reference. And we talk about references in chapter 7. But for now, think of references as, we had references in our Venn diagram of types. It is possible for, normally, if we're going to declare some int x equals 4, what else? Another thing we could do, let's say we make another int variable y, which is equal to x. That's one option, right? Another option is to make a reference, make that equal to x. And these look very similar, and in fact, the right-hand side is the same. So auto, if I was to do, auto w equals x, will always prioritize the type that isn't a reference. This one over here is a reference. And what is a reference exactly? We'll talk about that in chapter 7. But, you could argue that auto has the choice of either picking regular int or int ampersand, which means reference to int. It could pick either, because they both seem to kind of make sense in this context. Both of these are very valid. But it will never choose the reference. It'll never choose the reference. It'll always choose sort of just the normal thing without the ampersand on the end. Okay, so we have talked about already okay. The one extra thing I should mention, so we've said, if you're going to use auto, don't use the initializer list initialization method. Don't use initialization lists because the type we get is not expected. It's a bit unpredictable. Okay, so now looking at 6.3.6.2, auto and initialization lists. We talked about, generally if we're going to use auto, don't use initialization lists. Use equal sign because for initialization, because these lists can cause sort of an unexpected type deduction. But the other thing to mention is if we used an empty initializer, trying to get some kind of default value. So if we use the empty initializer, so like auto x and an empty initializer, normally, if it was int or if it was double, this would become 0 or 0.0. It would be the default value. But because we don't know what type, or at least because the compiler doesn't know what type we want, there's no way of knowing what the default value should be, and there's no way of knowing what type should be deduced. Right? We're in a bit of a jam. So this particular kind of line, where we use the empty initializer like this causes an error because there's just no way of doing any kind of deduction. There's no way of knowing what order should be translated to, what type, there's no way of knowing what type x should be. There's no way of knowing what this value should be. So we've got problems. So again, generally speaking, bottom line is just don't use these two together. Generally speaking, use an equal sign if you're going to use auto. Okay, so we talk a little bit more about the declarator type. And again, I wouldn't be too worried about this one just yet. I feel like it's not exactly an introductory thing. It's a bit more advanced, but DECL type specifier, but it is just something to note down. So yeah, for this we are deducing an expressions type without defining a new variable, right? Something new. So it takes in an expression. So DECL type takes in some kind of expression, and the thing to just note for now is it's most useful for generic programming, which is something mentioned a little bit further down the track, right? But it's just something to bear in mind, like, let's just say type, not type. When we start looking at generic programming, this guy makes a bit of a comeback, so it's good to keep him in mind for now. I have I don't think it's a very helpful example, so I don't think it's worth going into more detail than that. Just know that when generic programming comes up again, we're probably going to see this guy again. And know that in general, it takes in an expression and spits out the type. Maybe I'll show you one example that's like a bit more contrived. But for example, you could say int x equals 3. One potential use of this, and it's not a very useful use, but just to show a way it can work, is you might say decl type of x, y, just declare it. So what's happening here, well, it's taking an x, figuring out its type, int, right? This is the compiler doing this work. It figures out this is int, and therefore knows that y should be int. So it's another kind of replacement job where, like, this thing gets replaced with int. That's what that says. I don't know, it's not very clear. Int. This gets replaced with int because it takes in an expression, x in this case, and spits out a type. I believe you can also apply arithmetic operators because that would still be an expression. So, you know, if you do a division, that might make it a float or a double, sorry. You know, decimal number, I mean. You can do multiplication, probably still be an integer, things like that. So any kind of expression where you have some kind of entity involved, integers and whatnot, that would probably be something you can plug into declarative type. Alright, so now we move on to objects and values. That's fun. Alright, so now we move on to 6.4, which is called objects and values. So this part starts with a couple of definitions. The word object in particular can sometimes refer to a different concept that's a bit more specific. But in this context, the term object means essentially any entity that is stored into a contiguous, so one chunk of the light. Hang on. Any entity that is stored into a contiguous, so like a continuous chunk, contiguous region of memory. So you might have some memory that looks a bit like this, and you might throw in like an array, for example, an array with some numbers in here, 1, 2, 3, 4, 5. So this whole thing's your memory, and you've chucked an array into a continuous chunk of memory, so that array would be considered an object. Right? So that's an object, and then we've introduced this idea of an L value. Right? An L value is an expression that refers to an object. Right? So it's some kind of, usually we think of a name or an identifier, where when we use that name, we're referring to an object in memory. So, we think about int array equals 1, 2, 3, 4, 5. So that would be the L value. The A, this is ARR for array. That's the L value, which refers to this 1, 2, 3, 4, 5 array, which would have been stored in memory. That's the definition of L value. The L for L value refers to the word left, because generally speaking, and I think initially, these are called L values because you find them on the left-hand side of some kind of assignment or initialization. That's an equal sign. But that's not quite as true anymore in terms of technicality. Like, there are certain counterexamples where an L value isn't necessarily on the left-hand side of an assignment, but it's a pretty good rule of thumb still, this idea of left-hand side of an assignment, you'll find L values. There is an extra term called a modifiable. L value, which is essentially a specific type of L value. So an L value that has not been declared const. Right, so if I had said const int array, whatever, or maybe, can't remember how it works with arrays, but if I had said const int x equals 3, then this L value x, which has been declared with const, would not be modifiable because it's basically been declared as constant. We look at const a bit more in chapter 7, but without that const, then x is allowed to be modified, and so it is a modifiable L value. Okay, so we've introduced the term object, and we've introduced the term L value. And just for anyone who's been exposed to object-oriented programming, object in this context is not the same thing. Right? Object is simply anything that goes into memory. So now we look at 6.4.1, which is L values and R values. So we've defined L values already. The definition of an R value, that's fine. Definition of an R value, right? Instead of L for left, we have an R for right. So the essential definition, or the sort of summarized definition, is it's a value that is not an L value, right? So that's a bit, maybe not, doesn't seem so specific, but in essence, L values are values that refer to objects in memory. So R values are any values you see that don't refer to objects in memory. So typical examples include literals. Right, we talked about literals before. This idea of 3 characters C, whatever. So if I were to say int x equals 3, right, that it's the x which is going to be sort of associated with something in memory, right? You have this slab of memory. Some memory is going to be allocated for that x, and this line is saying apply or provide the value 3 in that memory. And if we were to say, x plus equals 1, what would happen? Well, we would go to the memory associated with x, right? We'd go to that object, and we would add 1 to it. This would become 4. But the 3 itself doesn't actually refer to anything in memory. The 3 is just a value that has been stored in memory. So that 3 we call an R value. And notice here that the 3 is on the right-hand side. So that pattern kind of still emerges. But yeah, in general, an R value is a value that is not an L value. It's not something that refers to something in memory. The easiest thing to think about for now is it's usually the thing that's being assigned to an L value. Literals are a good example. Okay, so there's 2 properties that we now want to look at, right? And these properties, there are 2 properties that we sort of use to describe objects. So 2 properties used to describe objects. Okay. So to describe objects. Okay. The first one is identity. An object can either have identity or it might not have identity. And what does it mean to have identity? If the program has a name, pointer to or address to, or some kind of, or a reference, pointers and references are more in chapter 7, to an object, then that object has identity, and in particular, we can use the name, pointer, address, or reference to let us. So identity lets us check if two objects are the same. Either the same in terms of value, or maybe the same in terms of memory address. Let us check if two objects are the same. Maybe that'll learn to write bigger. Are the same, right? So checking if their values are the same, checking if their actual position in memory is the same. In fact, if it's the same object, that's the point of identity. This idea of the ability to check if two things are the same is like quite an important part of it. Now, the next part I think is actually the bit that took me a while to wrap my head around. Even after I'd finished writing my notes, I was still a bit not super comfortable, because I don't really know if this concept is necessarily shown a lot in other languages. But the property of being movable, right? I think I'll give the kind of textbook notes first, or what I wrote down from the textbook, and then I'll also give an example of what it means to be movable. So the object may be moved from. We are allowed to move its value to another location and leave the object in a valid but unspecified state. And the chapter 17.5 is sort of mentioned, in the sense that this idea of valid but unspecified state is more explored there. But this might not make a lot of sense. I remember when I read it, didn't make a whole lot of sense, so I had to really do a lot of digging to sort of get a better idea. And I think what cracked it for me, at least, what kind of made it make a bit more sense for me, was working with a really concrete example. So I have some code that kind of goes to this, but I'll do this example in the board because I think it's important. So imagine you have code that looks a bit like this. So you start with, we have a string type, which is not a primitive type. It's not a type we went through. It's not a fundamental type, but it's a type where basically you join a bunch of characters together in an array to make sort of a word or a sentence, a collection of characters. So you can have a type string, and then I think I use like s equals, and then, well, in fact, we can use our new initializer thing, which is like the brackets, saying list initialization, saying a really long string. Imagine it's even longer than that. That's just so I can keep things short. But you have an S string, this really long string. So what does this look like in memory? Okay, we're going to work with memory here. So I'm going to draw two slabs of memory, because just to make things like really separate and really clear. But memory doesn't necessarily look like this. It's it's not just let's like snap them into pieces. But how this will work when the program runs is basically S is going to be associated with a particular address. So like on this side, S is going to be associated with some memory like this. So S is going to be over here, and then the string, really long string, is going to be over here somewhere. Some address over here. I might not write the entire thing, but you have like R, E, A, L, L, Y, and I don't have enough space to pretend we have enough to do the entire array of chars, right? Note that each char has 1 byte. So if we think about this in terms of a grid, each one of these spots here is 1 byte long, and each one of these has a unique address as well because it's 1 byte. So what does X actually hold in this memory, right? The S is kind of a label which corresponds to this this piece of memory, but what is actually in there? It's not the string, right? The string's over here. Well, the first character, this capital R here, will have some address, right? It's not clear, but it'll have some address like let's say 57, right? I'm abstracting what the addresses actually look like. They're actually very long hexadecimal looking things, but let's just say the address is 57. Well, S will store that address number, will store 57. So whenever you look up S, you'll see that address 57, and you'll look at address 57 and find the string. So I'm not going to bother with the 57 anymore. But essentially, S will store some address which will point to, spoilers on pointers, will point to the start of the string in this other piece of memory. Okay, so you got the S here, and then you got the string in a different place. So at first it might be like, why do we bother having these two different places? Like, why not just put the S and make it refer directly to this array? And hopefully will be clear in a second. Now, let's say we write something like string T is the same thing as S. Okay? String T is something as S. So the way this gets interpreted is, we have our S here. Well, we're going to have T be made on the same left-hand sort of panel of memory. So we're going to have T like this. T. And the question is, what should we do in terms of what should T sort of have access to? And one option is we could make T point to the same address, right? We could make T store the same address as what S does, so they both point to the same string of memory. The concern that C++ has with that is it is possible. Let's say if we do it like that, if we were to write T index 0 equals B or something, capital B as a character, what's going to happen? Well, we're going to look at T, we're going to find the data that it's associated with, and we're going to change the 0th index, so that first character, because we start counting from 0, to B. But then, if we try to print S, right, the string S, we're going to look at this, we're going to look here, we're going to look for the data, and we're going to see that it prints, it's going to result in printing the BALLY, right? And C++ is concerned, basically thinking that maybe if a programmer was to write it like this, they might not necessarily expect the S string to change as well as the T string, right? So out of kind of respect for the programmer, just in case if they weren't aware of this kind of behavior, what would happen? The compiler translates this as a copy operation, meaning the array over here gets completely copied. So this would have stayed as R, right? And then B, A, L, L, Y, and so on. B, E, A, L, L, Y, like. So maybe I should keep this as an R. Is it clear? Hopefully. That's a capital. They're both capital R's. They're both capital R's at the moment. That's not even a good R. They're both capital R's. So we copy. This is a copy operation. And this T will store the address of the newly made array. So it will be able to access the newly made array. So when we do T0 equals capital B, this element here will become B. And if we print S, this will result still in the original string because it was never altered, right? So straight up just doing like a T equals S kind of initialization causes a copy operation, which maybe is intentional, maybe is what is required, but copying in general is considered, especially for large data structures like strings, arrays, things that have a lot of bits to them, copying is considered very expensive computation because you've got to copy every single element. R's got to come across, then the E, then the A, like that, and so on. And if you've got a really, really, really long string, that's going to cause problems. So we have this move operation instead, and that's where this movable, it's taken me a while, but this is where the movable thing comes in. This idea that, imagine we had a kind of fancy operation that could, I suppose, force the T to link up with the original array instead of copying, right? So we call this operation the move operation. And let's say we say, so instead of this, we say T equals move, move of S. We'll do that for now. So what does this do? Well, move actually does a couple of extra things, but let's say for now, all move does is force T to link up with the first array. Now, C++ finds this problematic because S is an L value, right? S was, the name that referred to this object in memory. So S is an L value, which means if we just did that, if we just had S and T both refer to both referred to the string, then they both are kind of sharing ownership. And C++ doesn't really like that, right? C++ doesn't really, unless the programmer specifies that they want that, C++ doesn't think that's a good idea, right? So instead, move should only ever take in, move should only, this operation of T being linking up with the original string should only be applied to R values. You shouldn't be able to share ownership like this, which means S should kind of be kicked off. The ownership that S has over this string should be removed, should be severed. So what move actually also does is it will sever this connection. It will change the value stored in S, which was originally the address of the first string. It will change it to something else. Sometimes it's null. That part is the implementation defined. I think usually it's null, but sometimes it can just be some other random address. But we know that it won't be the address of the first character anymore. And so, essentially, what move does, what this function does, what this function does is it first turns the object in S into an R value by severing the connection between S and the object. So by object here, I'm talking about the array, and I'm saying what moves, the actual function that's built into the standard library, what it does is it first severs the connection between any L value and the object that it references, or it first refers to, and then T, and then afterwards, with this equal sign and referring to a variable, then returns the object for T to be the L value of. So hopefully it's clear that this is a more efficient way of making T equal this particular string, but you've got to be careful because S no longer refers to the string anymore. So if you're going to do this, if you're going to use this move operation, you've got to understand that S is no longer going to be involved. And this is where the valid but unspecified state is. S will no longer be linked up with the really string, so it's in an unspecified state, but it still exists. It's not gone. So you could actually reassign it, reassign it to like a new string. You might then say, S equals short string or something. You make it equal something else. But so movable, if something is movable, we are allowed to move its value, which is the string, from one location, which was the S, right? I guess its location was here, being linked up with S, and moved it to T. and leaving the object, which I guess was the S, in an unspecified state, a valid but unspecified state. So I guess when I think of moving, I think of ownership. We're moving ownership from S to T. That's how I kind of interpret it. It's my understanding of it. But that's the basic idea. So I think the major takeaways for now, hopefully that makes sense, but the major takeaways for now is this is a more efficient operation than copying, right? Rather than copying each individual string, all we do is we cut one connection and we make a new connection. And that's a much faster process. It's two things. You cut this, you do this, rather than copying however many characters you need to copy. It's more, so it's faster, but you do lose the S's connection with the string. That's important to remember. And you cannot, C++ will not straight up allow shared ownership. So in a sense, L values are not movable in the sense that if you're going to try and move an L value, it's first going to convert it into an R value by severing that connection, and then the R value will then be linked up with a new L value. Yeah, so T will then associate itself with the array. I'm hoping I'm using the terminology correctly. I'm not sure if I am, but I know that that's what happens in memory. I wrote programs to figure this out as well. I'm quite confident in that. I just don't know if I used those words correctly. But movable is that operation. Moving is that operation of changing ownership. Sort of kicking out one guy and replacing it with someone else. So those are the two properties we look at. We look at identity, right? Whether it has a name, and we can compare two objects. And movable, which is this idea of can we, in essence, change ownership? Can we change ownership for an object? So the idea is, if an object has identity, so if you have identity, so have identity and is not movable, then the object in question is an L value. Okay? So like, we're thinking of something that refers to something else in memory. It has identity because it's something that refers to something in memory, so there is an identity with that. You can check its values and compare it to other things. So it has identity, it's an L value, but it's not movable because, like we said, C++ isn't going to allow for shared ownership. So if you're going to try to provide an object with new ownership, but it already has ownership from an L value, right? So like that S has ownership with the string, has ownership of this string. We can't give T that same ownership. We can't move ownership for T because L still has the connection. So only after we sever that connection is T allowed to take ownership. But severing the connection makes the array, makes the string, an R value because there's no longer a name associated with it. So the L value itself is not movable. We can't sort of move ownership away from the L value in that way. But if it has identity and is movable, or it has no identity, so no identity, and is movable again, then it's an R value. So essentially, if it's movable, if you are able at the point where you can provide it with some ownership, then it's an R value. That's kind of the more, I guess, strict definitions of L value and R value. But I think this idea of, does it refer to an object in memory or does it not, is pretty standard. I'm a little bit unsure about the middle one at the moment because in my mind, if it has identity, then maybe it does have a name. But I think for now, I'm just focusing more on this part. If it's movable, if we can give it some ownership, then that's not a problem. For a bit more research, something I want to look into myself, there is slightly more specific words involved. The bottom one, if it's an object that is no identity and is movable, it's actually called a pure R value or PR value, which is pure R value. And if it is the middle one only, it's called an X value. So maybe if I look more into what an X value is specifically and what a PR value is specifically, I'll get a better idea about these different combinations. And there's one more term. If it has identity, so one of the first two, it's called a G value, which is a generic L value. So yeah, if it has identity, it's called G value. But in practice, L value and R value is what seems to be used most. So that's what I would focus on. But I am kind of curious what makes, if it has identity and it's movable, how that's an R value. I understand that because it's movable, I guess it's an R value, but having identity doesn't really sound like an R value kind of thing. But yeah, that's how I would describe that. How are we going? Oh god, that took half an hour. Okay. Okay. So that's on our L value, R value, and objects. Next, we look at lifetime, which is kind of goes hand in hand with scope, to be honest. But I think it's interesting to talk about this stuff. 6.4.2, the lifetime of objects. So when you think of the lifetime of an object, it starts when the object's constructor completes, right? So when we finish constructing the object, in terms of ints, for example, is that legible? Starts. Got it right there. I'm gonna waste ink this way. So the lifetime starts when a constructor, an object constructor, completes and ends, the lifetime ends when a destructor starts execution. Now, constructors, and especially destructors, I think, are not necessarily introductory content, but for now, think of for integers and like the fundamental types, think of a constructor as just like the basic, writing something into memory, writing the character into memory with its associated name, and then the destructor, just think of it as like a nothing kind of function that basically just like there's nothing to be done besides just removing the x, or like wiping out the x from memory. So like if we had int x equals 3, that's kind of construction. That's kind of like almost the constructor, but not exactly. But this idea of creating the variable is like the constructor. And then when the lifetime ends, usually because the variable is out of scope, and there's a destructor that does nothing except sort of wiping out the x and making it inaccessible. It's hard to talk about destructors without sort of going into more detail, I suppose. But that's a general idea. Constructor and destructor. And we can classify objects. We can classify objects based on the kind of lifetime it has. Based on how the lifetime is brought about. So we have this idea of automatic objects. Which basically usually have an object declared in a function. And I believe, so it's created when declared. When defined, not declared. It's created when defined and destroyed when out of scope. So when it's no longer accessible, that particular variable is gone, is destroyed. Now, whenever you call a function, so let's say you have like int f and there's a function. when you call that function with something like f, please, you call it, that function gets something called a stack. It's called a function stack? Stack frame, sorry. That function gets something called a stack frame. So imagine you have memory, right, for the program to work with and for the program to use. When you call f, a stack frame gets created, basically. So this is called a stack frame. And it's basically just a reserved kind of subset of the memory space for the function to use. So for example, if part of that function is int x equals 3, right, then some memory is going to be assigned and 3 is going to be plugged in there. Now, all this stuff happens inside the function, eventually returns, maybe returns, I don't know, x or something. That x might be returned back to the caller, but after it's returned, the entire stack frame gets wiped, basically. And that's kind of the destructor part. So that x sort of has a lifetime, so that starts here and ends when the function ends. Now, of course, in this case, the x gets returned, but unless you capture that x in a different variable in where you get called the f, so here in this case, unless you capture that variable like int, we can say even a different name, int y equals that f function. That return value is a temporary value. It's not really the same x, so to speak. It's that x got wiped, it's getting returned, and you have to capture it in a new variable that says int y equals f, the function f. You have to capture it if you want to continue to use it. So we re-discuss static objects, which I'm glad about. So static, these pens are getting quite light. I'm worried it's going to run out before I finish. That's alright. Objects declared in global or namespace scope. So I don't think I really talked about namespace scope, but for now, think about global scope. And you can use the keyword static before you declare something. Static declared, or static variables declared in functions or classes. What happens? Well, they're created and initialized once. Right, so that happens once. And they are destroyed, not when the function ends or when the scope is done, but they're destroyed when the program terminates. So when all the instructions that need to be done, when all the instructions in the program are done, that's when these objects are destroyed. Interestingly, they maintain the same address throughout the entire program's execution. And they are also, this is sort of more, again, not exactly introductory, but they are shared among all threads. So if you're gonna, make threads multi-threading, basically having multiple processes or parallelism running at the same time, you can. It's not like one thread has access to a static object and other threads don't. They all have access, and you typically require locking, which is essentially a way of making sure only one thread does operations on the static object at a time to avoid data races, where two threads, processes. Is that different? Two threads, essentially, two parallel running sort of bits of execution try to apply some operation on the same static object at the same time, and then cause some issues. Call it data errors. But anyway, that's for later. That's just something to bear in mind. But the big things to remember are they persist until the program terminates. That's like the most interesting one. I might get rid of lifetime as well. We then have free store objects. Basically, you can use the keywords new and delete. These are keywords. They're a little bit like malloc and free. They're a bit like that from C, if you're comfortable with that. But yeah, they basically allow us to create objects whose lifetimes are controlled sort of explicitly or directly. Like, if you can think about, like, the new is kind of like the constructor, and the delete is kind of like the destructor. When those things run and are finished, that indicates the lifetime of the object. It is mentioned that we explore this more in 11.2, chapter 11.2, so stay tuned for that, I guess. But for now, just understand that there are these keywords, new and delete, that lets us create objects and put them into memory explicitly. Like, we are asking for memory to be allocated, and then we are asking for that memory to be wiped away. Two more. We have temporary objects, which easiest place to talk about that. So usually we talk about intermediate results in computation. So for example, if you look at the code, that looks a bit like 5 plus 2 times 3. How is the computer going to handle that? Well, it can't just look at that and say 21, right? It has to actually do the computation step by step. So first things first, it's going to store the 5 and the 2 and do that first operation, that plus operation, to give us 7. And that 7, for example, is going to be a temporary object, right? Because once we multiply by 3 and get 21, there's no real way to reference the 7. There's no identifier, right? There's nothing. So maybe we say int x equals. In fact, all these things, 5, 2, 7, and then we make the 3 as well to multiply. Everything up till the 21, they're all temporary, because after they're finished, after we've finished competing with them, there's no way of referencing them. There's no way of saying, hey, let's get that 7 again using a variable. We can't get that exact 7. We can make a new 7. We can say int x equals 7, but it's not going to be the same 7 in the same memory address. It's going to be some other 7 that we pull out from somewhere. So that only that 21, we capture it in this int x. That's what that says. That's clear. Yeah. Only the 21 we get at the end. It is 21, right? So yeah. It's only that 21 at the end that we capture. That's the only thing that's non-temporary. It's a bit more persistent, stored in the x value. Everything else is a temporary value. So that's a typical use of temporary values, or temporary objects. There is this other one, but it uses references. Objects used to hold a value for a reference to a constant argument. I don't even know if I know what that means. Object used to hold a value for a reference to a constant argument. Object used to hold a value to a reference. I don't know if I'm taking it in even. Object used to hold a value for a reference to a constant argument. I don't know why that would be temporary. Alright, it's fine. For now, think of this. This is the main thing. In terms of lifetime, if bound to a reference, which I think is what that second example is about, to a reference, again, more chapter 7. Maybe I'll remember what it's about in chapter 7. The lifetime is that of the reference. So you actually don't really care about the object, you actually care about the reference to the object. It's something to do with if you have a value and you associate this idea of a reference object to that value, then the value is still temporary, but you have a reference to it. It's very strange. But more generally, and more clearly based on this example that I've put on the board, they will live, these temporary objects, they will live until the end of the full expression of which they are part. So in this case, the 5, 2, 7, and 3 will all exist. They will live, and then eventually the 21 will get computed and get associated with the x, and then all of these will be wiped out. Right? After the end of the full expression, the entire thing. Everything that needs to be computed is computed. And typically, generally speaking, temporary objects are automatic. Because generally, I guess they happen in functions and will be based on some definition. Now, more of a general statement. Oh, I know there's one more, isn't there? Before we get to this part. This thread local or something. Yeah. Thread local objects. So, objects that are declared as the light okay? Kind of got declared as thread local, and I have a reference here saying that this is chapter 42.2.8. So chapter 42.2.8 is when we know what that is. Declared as thread local. Such objects are created when their thread, like the particular stream of execution, is created and destroyed when their thread is destroyed. This is again, threads are not introductory at all, so not knowing what thread local means or what a thread is isn't necessarily the end of the world there. But essentially, you can have these different things called threads, which are like different streams of execution that can run at the same time, roughly. And I guess in one stream of execution, you can have a thread local object, which is sort of associated with that thread only. And it will be created when that thread is created, and it will be destroyed when that thread is destroyed. Alright, and then the last little bit to mention is array elements and non-static class members. So in general, these things are referring to objects that are like contained within like a meta object. So like you got array elements, which is stored within an array. Non-static class members. If you don't know what a class is, that's tricky, but essentially, think of maybe I should just say structs. I could probably explain it, but struct members. Non-static class members are kind of similar to struct members in the sense that they're like properties found within the actual object, but essentially smaller objects that are found within a more big object. These lifetimes they have lifetimes determined by the object of which they are part. So like if you have, this is part, so if you have like, some array, this array is an object, but it will also have elements in there. And you could argue that each element is an object. So what is the lifetime of these individual objects inside the array? Well, it's the same lifetime as the actual array itself. So that's the only extra thing to mention there. We're so close. Last 2 pages. Can I get it done before I pass out? Is type aliases. Now, what I will say about type aliases is if you're comfortable with the idea of type def in C, it's pretty much an equivalence. I can't really remember any reasons why there wouldn't be. It's type aliases. So essentially, the point of type aliases is to create a new name. It's a new name for an existing type. So think of a type that exists, right? Or an existing type. Think of a type that exists like int, right? Int is like oh god. That says existing type. For an existing type. Okay. That's better. Yeah, it's fine. That says existing type. Think of a type, and then, instead of int, if we wanted to call it bubblegum or something, we use the keyword using. So we might say something like using, I'll write big, using bubblegum equals int. Okay? And what does that do? How to use it? Well then, after, we could say int x equals 12, or we could say bubblegum x, I'll say y, just to not predefined technically, y equals 12, and they both do the same thing. At compilation time, right, when our translation is happening, it basically looks at all these aliases using bubblegum equals int, scans through. Every time it sees bubblegum, it will just basically do a find and replace. It will replace that with int, and in the eyes of the compiler, bubblegum is the same thing as int. It translates the same thing that int translates it. So, that's basically what that happens. So aliases are synonyms. So there's a kind of a transitivity property. So aliases are synonyms of the type they are aliasing. So that means they are synonyms of other aliases that refer to the same type. So what do I mean by that? Let's say, I'm not going to use bubblegum, it's a bit outrageous. Let's say I have using A1 equals int, and then using A2 is also int. I have something like A1 x equals 4, and then A2 y equals x. Well, for some, some people might think that, well, I know that they're the same type, they're both int, but maybe I want to keep my A1s and A2s separate. Maybe I don't want A1 to be able to be assigned to A2 because, I'd rather, there's a reason why, even though they reference the same thing, I have 2 aliases. Maybe I want the A1s to stick together, I want the A2s to stick together, and I don't want there to be any mixing. Unfortunately, if you think like that, that's not how it works. Because again, all the compiler does with aliases is it does a find and replace. Every time it sees A1, it just replaces it with int. Every time it sees A2, it just replaces it with int. And if we had this code, that's completely fine, right? We know that would work, no problem. X would get the value 4, Y would get the value that X has, which is just 4, so there's no problems there. So they both boil down to int, so there's no real problem. Now, what is the point of aliases? I believe there's a couple of reasons. Hang on. Okay. The reason that I remember, but I don't seem to have written it down, so maybe this is wrong, but the reason that I remember is especially if you have a really long type name. I was talking about it, might have been a couple hours ago, to be honest, but I was talking about, if you got like hash table, and then that hash table has types, and that type has types, like it can get really long, and maybe, you have to type it out once, but then you can give it an alias using, maybe just call it hash table if you've only got one type. Using hash table equals that really long hash table type, then you could just use hash table to then declare all the hash tables you want. Hopefully that makes sense. Like, you have some type that is really long to type. This type meaning type of data, this type meaning typing, like on a keyboard. You could say using, shorter name equals, and this really long name. And now every time you want to declare something that's of this type, you can use that one. So it can be a readability thing. There is also a really interesting point shown in the notes, which is like you can use aliases to help you with portability. Portability meaning, if you've got two different machines that work slightly differently, for example, their integer sizes are different, you can actually kind of use aliases to kind of get around that. So I'll show you the kind of example code that was in the book. So imagine you have two machines. So imagine having two machines. One machine, so machine A, has 32-bit integers, right? So it assigns 32 bits if you're going to read an integer. And the machine B has 16-bit ints, but it has 32-bit longs. Okay? So imagine we have code that looks a bit like, I don't really remember what's a good value, but something that takes 32 bits, basically. Int x equals, I forget the exact number, like 2 billion or something. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. My point remains the same. I can't remember exactly what the values are. I believe this would fit in 32 bits, but it would not fit in 16 bits. So what does that mean? If machine A reads this line, there's absolutely no problem. It can fit that in 32 bits because that's how many bits that are available for an int type. However, machine B would have problems because you're trying to fit a 32-bit integer into a 16-bit thing, right? Into 16 bits. And because it sees that keyword int, it's going to only use 16 bits. And that's what results in something called a integer overflow, where you basically try to fit too much stuff, too much data into too few bits. So that would cause problems. However, what can we do instead? We can start the program, instead of just straight away reading in the x value, we can start with an if-else branch. If the size of int is equal to 4, right? We do 4 because size of is like a function that is, it's not readable, I'll do it bigger. Size of is a function in C++, and I think it's in C as well, that, is it a function? It's like kind of, it's basically a function, takes an input, spits out output. If size of, it takes in like a type, and it spits out the size of that type in bytes. So, we typically think 8 bits is 1 byte, so 32 bits will be 4 bytes. So if we have a machine where the size of int is 4 bytes, then we'll make an alias that's like using int 32t equals int. Got braces, that's why. It'll look weird. Else if size of long equals 4 bytes, then, wait, is that right? Yeah, it is. Yeah. Else if this long is then using int 32t equals long, and then it would end. And now we can use the alias int 32t x equals to 2 billion. And essentially, the first machine, machine A, would replace int 32 with just regular int, right? So that would say int x, and therefore would assign 32 bits like before, no problems, can fit 2 billion in 32 bits. Here, for machine B, int 32t would not be replaced by this first one, would actually be replaced by long. So you get long x equals 2 billion, and long is given 32 bits to work with, so that would work too. So you can actually use type aliases, sorry. You can actually use type aliases to improve portability, right? Allow the same code to work on 2 different machines. Yeah. Now, the general convention is the underscore t typically is used to indicate an alias. Did I mention there's a library that I think it's, hang on, I think the library is, did I have it somewhere else? Hang on, I can find it. It was in my notes for sure. It's somewhere. Sorry, wasting time now, but there's the one. C standard int. I think I might have mentioned it before as well. But this library basically makes these kind of types, these alias types, out of your basic machine architecture. So in this case, you wouldn't have to do this because there's a library for it, but the general idea stays the same. And this library does this convention of like underscore t being used for aliases. So we have that. Yeah. Okay. The last bit I will say before we wrap up. Oh, last 2 bits actually. Naming an alias after its representation. So naming an alias after its representation. So for example, calling an alias int 32 can be problematic. Obviously, that standard library I just talked about does this, but the purpose of the alias is to be 32 bits, so that's kind of okay. But generally, we want to name an alias. Name an alias after its purpose, and the reason for that is suppose we make an alias and we call it int32t. That's great and all, but what if we realize down the track that we actually want to store 64 bits, right? It's not a huge deal, but you would have to change all the places you mentioned in 32 into 64, when in reality that's not really something you should have to change. Wanting to change from one number of bits to another, you might have to say using this alias equals long instead of equals int, and that's fine. But having to actually change every single time you mention the alias is annoying. So it's better to just call it like, to be honest, int is probably a bad example, but in general, it's better to name an alias after its purpose rather than its representation, rather than going into really a lot of detail about how it's represented. Now, the last thing I'll talk about before we wrap up, we cannot apply type specifiers like unsigned to an alias. Unfortunately, I think this might be where the find and replace analogy breaks down. Yeah, so imagine we make an alias like using capital char equals char. Don't know why you would do this, but just for the sake of example. Unfortunately, if we wanted to make an unsigned char alias, if we were to try this, where we use the unsigned keyword in front of the alias char as opposed to the original char, that would not be, that would cause an error, unfortunately. I'm not too sure why, to be honest, because I feel like with my find and replacing in mind, like you'd just expect that to be changed. But I guess in general, there's just this rule that's been applied where you cannot apply type specifiers. There's an expectation that an entire type will be mentioned or will be stored within the char. So when you try to change it with type specifiers like unsigned, it causes problems. So if you wanted to make an unsigned char, alias, for example, you would have to use all the original types, so unsigned and lowercase char. All right, and I think that took about an hour, so that should be, I think overall it's like a 4-hour video, so that's fun. Anyway, yeah, hope that was helpful.